Okay, we are live in YouTube now. And we are recording here. So I guess we can start. Let me just set. Okay. Okay, so good morning, ladies and gentlemen, members of Bingo Collaboration, professors, students, and people following us live in our broadcast here at Zoom Room and in YouTube. My name is João Rafael, and it's a pleasure and honor to be here as your chair today. And we say welcome to the second day of the Bingo Radio Telescope event, launching the portal and project updates. Today we have several seminars covering the different stages of Bingo project. So if you want to know more about each stage of Bingo, you can visit us at our website, bingotelescope.org, and see our science section. It's a great pleasure to start our second day of activities with a colloquium presented by Professor Bing Wang. So Professor Bing Wang earned his PhD from Fudan University, and he's also did a postdoc at University of São Paulo in Brazil. He is one of the PIs of Bingo Collaboration, and director of the Center for Gravitation and Cosmology at Yangzhou University. He's also distinguished professor at Shanghai Jiaotong University. Sorry if I'm pronouncing wrong. He's one of the initiative and core members of Bingo, and his leadership in China and friendship with Brazilians allows us to make Bingo more international. So let's welcome Professor Bing Wang and see his nice presentation, Listen to Universe. So Professor Bing Wang, thank you so much again for everything. The word is yours.
Thank you, Joe, for your very nice introduction. And actually, I'm very happy to give this colloquium in this meeting. Good morning, everybody. I'm very happy to serve in this Bingo collaboration. So I'm going to talk about this, maybe it's too easy topic to many experts. So I'm going to talk about the listening to the universe. And when we talk about the gravity, so we remember our old Chinese idioms. So that was an idiom about a person in the country called Qi country. That was 2000 years BC. And that time, this person worried about the collapse of the star to our Earth, falling down of the star to the Earth will destroy our Earth. But that way of thinking, it's related to the gravity. But he was not encouraged to think more deeply to this gravity theory. And he was even considered to be a worrywart. And people laughed at him because people think that he borrowed trouble and anticipate that may never happen, never appear. So if he was encouraged to think more deeply, starting from that period of time, 2000 years BC, maybe we already know about the gravity. That's a joke. I'm just talking about this gravity and cosmology was important, was interesting since that period of time. And it is interesting nowadays on this gravity and cosmology because we have very nice topics because this theory of gravity basically covers the very wide range of physics from the subatomic range to the far reach of the universe. It covers a lot of interesting topics from Big Bang, black hole, accretion disk, blah, blah, a lot of things. And especially because recently the great achievement in the achievement in the modern technology. We have CMB observation, we have different satellites to detect precisely on the CMB spectrum. We have gamma ray burst observers. We have a lot of, even nowadays, we have the gravitational wave detectors. So these help us that we understand more on this gravity and cosmology, make these interesting topic even more interesting. And when we think about gravity, we will never forget Einstein, because Einstein has contributed a lot to this theory of gravity. In Einstein's relativity, he has three startling predictions. Einstein told us that our universe was expanded from a Big Bang until now. It evolved until now. Einstein told us that in our universe, there is an exotic object called a black hole. And Einstein also told us that in the universe, we have such kind of a mysterious dark energy, which can act against the pull of the gravity. All these three startling predictions of Einstein's relativity was confirmed. For example, our universe started from a Big Bang through the expansion. This actually was confirmed by Hubble in 1929 through observing of the galaxies running away from us. Further away, it's running away even faster. So this basically tells us, implies that our universe started from a Big Bang and expanded until now. Also started from the 1970s, people already have some observational signatures on the existence of these exotic objects in our universe, the black hole. Especially nowadays, we know more on the evidences of the black hole existence through Chandra satellite, X-ray observation, through gravitational wave detection, through Event Horizon Telescope. And also in 1998, from supernova type 1a observation, also people confirmed Einstein's third prediction that our universe can enter accelerated expansion. But Einstein's legacy is incomplete. His theory fails to explain the underlying physics of very phenomena his work predicted. For example, he predicted about the Big Bang, and our universe started from the Big Bang. But what powered the Big Bang? We don't know. We cannot find answer in Einstein's book of general relativity. Einstein predicted existence of black hole, but what happens at the age of the black hole? We don't know. Even until now, we don't have the answer in Einstein's general relativity. Also, Einstein predicted about the existence of dark energy, which can drive the universe into the accelerated expansion. But what is this mysterious dark energy pulling the universe apart? We don't know. So all these questions in our mind that we are seeking the answer is that this can help us. If we can answer all these actions, we can go beyond Einstein. We can even answer something that Einstein, he himself, cannot answer in his book. So this is actually what we want to do in this new century. Especially we want to encourage young people to, when they join this field, to do more. So how to answer Einstein's, let me just talk about the black hole. What's the physics at the vicinity, happens at the vicinity of the black hole? This we don't know. How can we get the answer on this? We have to listen to the black hole. One way is through the gravitational wave detection. Actually, in LIGO gravitational wave observation, people have already heard the sound of the black hole, and this is the wave of the sound of the black hole happening at the vicinity of the black hole. And it was announced, the result was announced in February of 2016, and got a Nobel Prize the second year, 2017. Nowadays, we have a lot of evidences of black hole collision and neutron star collision. Even now, we have the black hole and neutron star collision gravitational wave released from these collision. And winning the Nobel Prize is not the end story of listening to the black hole. We want to get more information. We have to listen to the millihertz sound of the gravitational wave. In this millihertz sound, this can be more physics included. For example, it can include supermassive black hole collision. It can include this EMRI, this extreme mass ratio differences, black hole collision. And even it can tell us about the process of how these two binary black holes coming together, closer, and finally it can merge. So it can tell us the more information. And this kind of millihertz gravitational wave detection will count on the space gravitational wave observatories. Nowadays, in our world, we have LISA in Europe is developing, is preparing for the launch in 2030s. And also in China, we have two projects, Tianqing and Tianlai. Tianqing, in Chinese, it means a harp, a musical instrument that is waiting for the plug of the string, plug the string by the gravitational wave, can produce the sound, can be listened by us. And Tianqing is the different design from LISA. Tianqing is the 3 satellites moving around the Earth, is in the Earth orbit. And the Taiji is similar to LISA. It will moving around the sun. But Taiji has, for these satellites, it has longer arms. This can help us to detect the gravitational wave at the lower frequency, even to the higher precision. And for Tianqing, because it's running around the Earth and the arm is shorter, so Tianqing is more useful to detect the a little bit higher frequency, so it can bridge the gap between LISA and the LIGO. So these are the 3 space gravitational wave observatories are being built, and in the future can help us to listen to the black hole, can help us to answer the question on what's happening at the vicinity of the black hole. What's the physics there? This has not been answered by Einstein, and hope this we can, through answering these questions, through the observing, listening to the gravitational wave sound, can help us go beyond Einstein in the understanding about the black hole. And also we want to listen to the universe. So here I just give a brief introduction on the history of the universe. So we know that the universe started from a Big Bang, and in a tiny fraction of a second, the universe experienced the inflation, exponentially expansion. And in this process, the universe becomes very cold. And in this process, because of the quantum fluctuation, and this fluctuation will evolve, will grow, and finally will go out of the horizon to be frozen, and then re-enter the horizon, become the classical seed of the particles of the contents of the universe. And on these quantum fluctuation seed, it will develop a certain elementary particles, for example, photon, neutron, electron, all these particles. And at that time, due to this quantum fluctuation in the end of the inflation, and this universe will be reheated. And after the reheating, all these elementary particles will move freely in the whole universe. So the universe was like a soup. So the photon cannot run away from this soup. There is no free path for the photon to run away from this soup. So we cannot look understand the universe at that early period of time through observing the photons. Because photon, when it runs to the east, it will bump into the electron, run to the west, probably will bump into the neutron. So we cannot count on the photon to tell us the story about the very early of the universe. Only later on, when the universe continues to expand, the universe temperature will start to drop, and then we have such kind of recombination. For example, like neutron and proton will form a nucleus, and then will attract the electron to move around it. Step by step, it will have the free pass for the photon and to travel. So the universe will start step by step to become transparent. When the universe was 380,000 years old, it's already completely transparent, so that the photon can travel inside the universe. So we can count on the photon to understand the universe when she was already 380 years old. We cannot, as the reason I explained to you, we cannot count on the looking at the photon to understand the universe even earlier, because that time, as I explained to you, the photon doesn't have the have the free pass to travel. So we don't know. We cannot look at the universe through photons. So all these photon signal we can know is starting from the universe was already 380,000 years old. And this is the CMB we observe. From the photon, we observe this cosmic background radiation. And afterwards, in the universe expansion period process, it will become, temperature will drop. And then we have step by step, we will form the structure like a galaxy cluster, step by step. We have the universe nowadays. So the age of the universe nowadays is 13.7 billion years old. So this is basically the history of the universe. And we have a lot of proof to tell us that this kind of theory is correct. One is that the hot Big Bang universe at the very beginning, as I mentioned, we only have the neutron and proton, and then from the neutron and proton, we can form this hydrogen and helium, and then step by step we have lithium. So this is the can tell us about the nuclear synthesis story, and this nuclear synthesis story basically can be confirmed by observations, and basically observations really confirm this primordial nuclear synthesis theory in this model I just explained to you briefly. Not only this, before that I also mentioned about the Hubble law. It has already been confirmed in 1929 by Hubble. So these laws, these evidences, also including later on I'm going to explain to you on the cosmic background radiation observational results, and also about the structural formation of the universe. All these four pillars basically shows us that our understanding of the universe is correct. Our theory on this Big Bang cosmology is correct. And talk about the cosmic background radiation, we have to remember these two gentlemen. Basically, they are radiophysicists. That time in the 60s, they were building a kind of telescope in New Jersey. They tried their best to cancel the noises in this telescope, but they cannot. So they asked these physicists in Princeton, and finally, these noises, they cannot cancel, they cannot remove it. That's the noise of the cosmic background radiation. They published the paper in the same journal, same issue of the journal, fortunately that they got the Nobel Prize. The people's he already contributed a lot to the theory of cosmic background radiation. He won the Nobel Prize only in 2019, and later on, people have spent a lot of energy, a lot of money because of the improvement of the technology. So people started to observe the cosmic background radiation not only on the ground, but also launch a satellite to detect such a kind of cosmic background radiation, to listen to the universe, to the early universe when it was 380,000 years old. And these two principal investigators, they actually led the COBE satellite project. So because of their contribution, and that time they already detected to the precision 10 to the -5 level. So it marked that the cosmology becomes a science, becomes the precision cosmology. So because of this reason, they won the 2006 Nobel Prize in Physics. And later on, people go on to study about the cosmic background radiation. People launched this WMAP satellite, and comparing to COBE satellite, you see that the COBE satellite, like an infant looking at the sky. The infant, we know that usually doesn't have a good eyesight after he was just born. So he look at the universe with his eyes, but that's not clear. But the WMAP case gives us even more precise result on the universe. And also we have Planck satellite can help us even listen to very tiny, very detailed sound of the universe. So through the cosmic background radiation, we can listen to the universe when it was 380,000 years old. And also because of the precision of this experiment, we can have a very nice sound, very good music, very nice quality music of this universe, early universe. So this is actually what the picture, or we can see the portrait, or we can say this sound record of the universe when it was 380,000 years old. And because of his contribution to the CMB theory, and the peoples won the Nobel Prize in 2019. So, but from the CMB, as I mentioned to you, that we cannot count on CMB to answer the question that Einstein, he himself has not answered. For example, what powered the Big Bang? We cannot count on the CMB because, as the reason I told you, that the universe became transparent when it was only 380,000 years old. Before that, it was opaque. We cannot count on the light to see the universe. So how can we answer the question that Einstein has not answered? We have to count on the gravitational wave. We have to listen to the gravitational wave so that we can answer the question, what's the earliest moment of the universe? What's the physics there? And in 2014, the Hubble Smithsonian Center of Astrophysics, they have the press conference. They released the news. They claimed that in BICEP2 observation, they have observed the primordial gravitational wave. So they claim that they have listened to the like infant song, the baby's first cry of the universe. So they claim that news. But unfortunately, the result was proved incorrect because they haven't removed completely the foreground noise. But we know that the physics is there, is that when in the inflation, we have the density perturbation And also we have the tensor perturbation, gravitational wave perturbation. And because of these perturbations and the radiational field around the electron become quadrupole. And in the density perturbation, this kind of quadrupole will not be twisted. But in the tensor perturbation, the gravitational wave perturbation, it will be twisted to become a curve, like a curve shape. So here, here I showed you this blue and the red. It has different anti-clockwise or clockwise curve. And this is the, we call this B mode of CMB. This basically can tells us about the signature of the gravitational wave, primordial gravitational wave at the very beginning of the universe in the inflation. So once we observe the CMB B modes, basically this can help us to get the information, get a signature of the gravitational wave, primordial gravitational wave in the very beginning of the universe. But the observing of the B mode, the CMB B mode, is very difficult because from the figures I showed you, this B mode is very weak. The signal is very weak compared to E mode. The B mode is very weak. This actually tells us that it's so difficult to really detect such kind of B mode in the very strong foreground noise. How can we get such kind of signal? How can we listen to the sound in the huge noise? How can we catch the sound? So it's very difficult. So this is the BICEP 2 experiment. Now they are doing BICEP 3 observations. And this dark sector lab located 3/4 of a mile from the geographic South Pole. And beside it, there is a kind of a South Pole telescope already have contributed a lot to the observation of CMB, especially at the small scale. And not only in the south hemisphere, in the South Pole, but also nowadays we have in the North Hemisphere, in China, in Tibet, we have ALI CMB polarization telescope. Actually, Larissa Santos, she also joined such Chinese ALI CMB polarization telescope. So we hope that in the future, not only in the South Hemisphere, but also in the North Hemisphere, we can listen to the sound of the universe at the very beginning. And this can help us to answer the question that Einstein has not answered. What's really happening at the beginning of the universe? What power the Big Bang? And now let me jump to this dark age. We know that after the CMB, after the universe become completely transparent, after we have the CMB signal, when the universe was 380,000 years old, or redshift like 1,000, until the first star was formed. So we have a certain period of time, certain period of time, the universe, we don't have any signal of the universe. We don't know what's happening at that moment. This was called a dark age. The experimental way to detect what's happening in this dark age is only hopefully through observation of 21 centimeter of the neutral hydrogen, because the neutral hydrogen is the most abundant bionic matter in that period of time. So we hopefully that we can understand about the dark age of the universe only at this moment through this 21 centimeter radiation in the neutral hydrogen. So already nowadays we have some kind of result from EDGE experiment, and this already told us about what's happening at the redshift around 18 or 17, and this observational result, it has some discrepancies from the lambda CDM model prediction at that period of time. And We have a lot of models try to alleviate such kind of problems between the observational data from age and then the CDM model prediction. So hopefully in the future, we can have more data to understand more on the dark age. Another period of time we don't know a lot of the universe evolution is the accelerated expansion. We don't know what's the dark age, although people claim that this kind of accelerated expansion of the universe was driven by the dark energy. And the simplest explanation is the cosmological constant played a role as the dark energy. And this dark energy makes up like 70% of the universe compact, but we don't know what it is, what is the nature of this dark energy. The first detection of this acceleration of the universe was because of these three astrophysicists, because of their discovery of the distant supernova type 1a. And they found that our universe is experiencing accelerated expansion. And but we don't know, as I mentioned, that who is driving, what kind of force is driving such kind of accelerated expansion of the universe. And only for we physicists, we don't have that imagination. We only can think about understand this kind of accelerated expansion from Einstein's equation. Either we modify gravity or we modify the matter field. So we don't have the clear picture on what's the physics behind such kind of accelerated expansion. Nowadays, the current situation is that like a blind people touching the elephant, we catch the tail. Probably we think that it's the quintessence model plays the role, or we touch the trunk. Maybe we think that it's the FR model, modified gravity. We don't know what's the real physics. How can we know? We cannot completely count on supernova type 1a, because supernova type 1a, there is no enough confidence from this supernova type 1a tells about the real physics of the universe expansion, accelerated expansion, because supernova type 1a itself, whether it can really be considered as the standard candle, it is a question, because still we have nuclear physics. We have to understand more clearly about what's the real reason for this kind of supernova type 1a explosion, and whether this kind of energy released, it is that standard, to how high precision it is standard candle. So this is one question. Another question is that through this long distance, whether this light can travel in a straight line, or it will be because of lensing or weak lens, gravitational lensing, it will be changed the path. We don't know. So the distance measurement is that precise? This is a question to be asked. Also, this telescope systematic error we have to consider seriously. So if we consider these kind of systematic errors, systematic effects, so only count on supernova type 1a, we cannot really answer the question, what the universe expansion. We have to use the complementary observation. For example, if we really want to open the door to understand the physics of dark energy, we cannot only count on supernova type 1a. We have to open the door simultaneously. For example, we have to understand from CMB, from cluster, mass of the cluster, number of galaxy cluster, kinetics unit, velocity effect, redshift distortion, etc., etc. Especially important is that whether we can understand it from the 21 centimeter radiation from the neutral hydrogen. This is also important locker. We have to open it so that we can really understand about the physics of dark energy. And we know that for the bioacoustic oscillations, And this is the recorder of the large-scale structure. And in the Halley universe, photon and the baryons, they are coupled, and they form a high temperature or high density photon baryon fluid. And the density fluctuation will transmit as waves in the fluid. This will form this baryonic oscillation, baryon acoustic oscillation. And this BAO will exist in CMB. It will exist in large-scale structure. This BAO can be considered as a detector or be considered as the standard ruler, can help us to measure the expansion of the universe. So that measuring this BAO basically plays the important role in constraining models, in helping us to understanding about the physics of dark energy. So this is so important for us to measuring BAO. And there are two different ways to measure BAO. One is from the optical measurements, but optical measurements, it has some drawbacks because optical measurements, it need this 3D dimension map of galaxies. It needs large scale of the 3D map of the galaxies. And this is difficult to obtain. And also, this can only be used to measure the BAO at very small redshift. So at this moment, only we can measure the BAO through optical measurement until the redshift equals to 2. And still, it has the big error bars. So we cannot only count on optical measurement of BAO to understand about this physics, to understand about the structure, understand about the large-scale structure of the universe. Well, there is another way to detect this BAO is through the radio observation. And this is considered to be the powerful way. And especially this radio observation will be very important, very useful, because it can help us to understand even earlier a period of time of the universe. Because when redshift is high, we still can use radio observation to detect the BAO. So that's actually, we hope that this can be realized in this 21 centimeter observation. And nowadays, we have existing projects in China. We have FAST with this 500 diameter big single telescope. And this will be used to detect this BAO as well. And also in the future, we have this SKA. And also we have some other experiments in the world. And our bingo experiment is more important because it's concentrating on this universe when it has already entered accelerated expansion. So in the bingo observations, bingo telescope, we can really disclose about the BAO when the universe has already started acceleration. And this can help us once we have the data, once we can understand the data of the observation. This can help us really help us to understand the nature of dark energy. So this is the importance why bingo project is that important. So I just want to emphasize it. And this is the international collaboration led by Elsul Abdallah. And we have several different institutions in the world join this project. As I mentioned that we have to listen to the universe to answer these questions. This was classified, this was ranked as the top questions to be solved in the 21st century. Underlined in yellow, they are all related to gravity and the cosmology, to our field. So this is also why nowadays gravity and cosmology are so important to be studied by the young people. Especially nowadays because of the modern technology. We have a lot of modern technology helps us to make sure that we can have a great achievement in the future to understand about our universe. For example, we have CMB, and we have the gravitational wave detectors, and we have a lot of other experiments are being done or will be done in the future. Bingo radio telescope is one of them, and we hope that through Bingo telescope can help us to understand about the nature of dark energy and have some breakthrough result. And this is the statue in Washington, and we see that the people, young people in different colors sitting beside Einstein, and we know that we have a lot of questions to be asked. For example, how did the universe begin? Does time has beginning or an end? And why we have this kind of accelerated expansion? So there is no more important task before us than education and inspiration. So we hope that through these 2 days colloquium and introduction programs, we can attract more young people to join us to work in the field of gravitation and cosmology. It is very promising. Finally, I use these 4 golden lessons by Steven Weinberg, the Nobel Prize winner in 1979. He mentioned that one I emphasize in blue is that he mentioned that go for the masses, exploring the unclear, uncharted areas of sciences can lead to creative work. So this is a good lesson actually to young people, not only to young people, to ourselves as well. And this 21 centimeter cosmology, until now, still we don't have the data. We don't know what's the physics there. And this is the field described by Weinberg as the massive, because in Chinese also we have the idiom that if the water is clear, there is no fish you can waiting for you to catch, because all fish has already been taken away, has already been caught. So only you can find a fish. You can do a good harvest to hooking the fish. It's only in the unclear water. Probably you have the chance. In studying physics, it's the same. That only in these field still are unclear. They have chances for you to do some good work. So this is the last slide I just want to show you. Is that I hope that through these 2 days introduction lectures, I hope that more young people will join this Bingo project, will contribute to physics and help to go beyond Einstein to answer all these questions that Einstein he himself cannot answer. I hope that you can make a great achievement in studying physics, in exploring the universe. Okay, thank you very much.
Okay, thank you so much, Professor Bing, for such a nice talk, such a nice colloquy. It was really beautiful. So I'd like to invite our audience to make some questions. So if you have any question here in Zoom, you can turn on your microphone and ask the question to Professor Bing. And also, if anyone has any question in YouTube chat, you can also type the question there in YouTube chat, and we are going to send to Professor Bing. So I'm going to talk this in Portuguese, because maybe we have some audience in Portuguese. Então, pessoal, se vocês tiverem alguma questão para a palestra do professor Bing, podem ficar à vontade para fazer. Se vocês tiverem alguma questão aqui na sala do Zoom, vocês podem digitar ou então falar a questão em português através do microfone e a gente vai fazer a tradução da melhor forma possível. Well, I have one question.
There's one question in Zoom from
okay.
João.
Oh, let's start from the audience. So João Alberto is asking, could you talk a little bit more about the advantage of radio observations of BAO over the optical observations?
As one benefit, as I mentioned already, is that through the radio observation, we can understand, we can detect the BAO even earlier. Because optical measurement, we need a large-scale scan of the sky. And the radio telescope, and this has the problem, difficulty, and also for the optical measurement, it has limitation, is that we can only detect the BAO at the small redshift. But until now, we have the redshift 2. So still in redshift 2, this BAO detection in optical measurement, it has the bigger error, like 2.5 sigma error. And we hope that in the radio observation, we can detect the BAO at a larger, bigger redshift, so that we can know what it is the physics when the universe just starts the acceleration, like redshift 0.4648. This is the bingo range. So this is the benefit of detecting BAO through radio observation. Thank you.
Mais questões, pessoal? Is there any more questions for Professor Beam? People are a little bit shy, I guess.
It's too easy. I understand, because this is to all the experts. The talk is too easy. So we can move on, I think.
Well, I have a question, in fact. Well, I like it a lot, the approach you did, Professor Bean, talking about how you can listen to the universe, because and showing different kind of experiments, because it's like, well, each experiment has or provide us its own music about the universe, because we are seeing different frequencies or different wavelengths. So what I was going to ask is, once we, let's say in Bingo, for instance, that would like to study BAO at a specific range of redshift. So what could be a nice music for Bingo, let's say? What could be a nice result that we could see about the dynamics of the dark energy from Bingo observations?
This is a very good question. Actually, we really want to understand this physics of the universe. And in Andres' talk, I think he will introduce more carefully on how to use Bingo to understand about dark energy, including the dynamic dark energy, also including this dark energy interacting with dark matter. So it can appear some signature inside this BAO or 21 centimeter radiation from the neutral hydrogen detected in the future by Bingo. So this is a very nice question. Actually, we are waiting to see the result. And also you mentioned about, I just combine all these things. I use the title Listening to the Universe. There are a lot of songs to be listened. As I mentioned to you, discuss with you, this gravitational wave, This is also very interesting topic. And SKA, we hope that it can also contribute to the gravitational wave detection, probably. And I think also it has some similar physics, for example, foreground removal in the gravitational wave, also in the primordial gravitational wave. It has the foreground similar to the 21 centimeter signal. So that's the reason Larissa Santos, she is working also in the ALI primordial gravitational wave project using her expertise. She can also contribute to that project.
Yes, this is amazing. We are seeing now a different kind of spectrum to the gravitational waves. It's a gravitational spectrum. So this is really, really interesting.
Yeah.
Thank you. Thank you so much, Professor Bing.
Thank you. Thank you very much.
It was really a pleasure. It was an honor. And again, I would like to thank you for everything you did there in China in these days and the contributions for our event.
Thanks a lot. I would like to thank Elcio, actually. He has contributed a lot on this. For example, I'm always saying that he's young, always young, because you know, leading this project is not easy, especially, I don't want to say this word, but I have to say, at his age, his reputation, he's famous. So he is leading such a big project. It's a kind of a challenging work. It is very difficult, and he has contributed a lot. So I would like to thank Elcio for all his contribution to the Brazilian, to this international science.
Thank you, Bin. Nothing would have been possible without all my collaborators today. We have 100 people working, and you are doing also a wonderful job. Thank you.
Okay, so I guess we can move on to our next speaker. So I'd like to invite our next speaker to share his screen with us. It is Jiajun Zhang.
Hello.
Hello, Jiajun.
Yeah, thanks for the introduction.
So let me just introduce you a little bit better. So Jiajun, he's postdoc at the CPTU Institute for Basic Science in Korea. He is also member of the Bingo collaboration and representing the scientific management as stage 3 team. He's going to present us today a seminar titled Simulate Bingo Expected Signal. So Jiajun, thank you so much for being here. Thank you so much for all your help. The word is yours. And again, we are honored to have your presence here. So thank you.
Thanks, John, for the introduction. And I'm also very happy to be collaborating with so many good friends and colleagues in the Bingo collaboration. Thanks for everyone's contribution. So I will start talking about the simulate bingo expected signal here. We know that the key goal of bingo was trying to detect the BAO signal, and which is trying to detect it using the 21 centimeter line and using the so-called intensity mapping technique. So the whole outline here was I will give an overview about the technique of 21 centimeter intensity mapping itself and how we can make a mock map or a mock observation of the 21 centimeter intensity mapping and several of the tests we have done here. And all this work was based on the paper we have already put on arXiv yesterday, the Bingo Project 6 paper. Welcome to read it for more details. So let me give a very brief overview about the mocks itself. So why do we want to build a mock? Just like what Professor Wang has told us that we can listen to the universe in many different ways. For example, 21 centimeter is one of the way. But how do we know that using our technique, using our telescope, using our software, using our pipeline, we can really find the correct cosmological signal? That is the key question that Building MOC could really solve. What a MOC mean was that given a cosmological model, for example, here we're using the standard cosmological model, lambda CDM model. Based on such a kind of model, we can run a simulation in the computer to simulate the structure formation process of the universe, and then put in some H1 gas, so the neutral hydrogen gas, which will emit 21 centimeter, and then assume that we are in such kind of a simulated universe, and we do an observation in this universe, then it would provide a very nice MOC data, and that MOC data could give us a challenge to say whether our data analysis pipeline could really see the proper cosmological signal we are looking for. And another key point is that because we don't really understand what is the systematics error inside of our software, inside our design, and so on and so forth. So what we can do is that we are using the computer, we can ask computer to generate hundreds or thousands of different universes at the same time. So we can try to observe many different universes and take an average of those. And we can also find the standard deviation of that would tell us what is the error of our design. So currently, today I will introduce you about just the signal of the map itself, the 21 centimeter signal from extragalactic H1 gas. A full MOC actually not only consists of signal, it will have the signal, that is what we would like to see, that is the expected signal. But we will have some other things that we don't really want to see. For example, the foreground is a contamination from our own galaxy. We'll have also all kinds of noise, like the equipment itself and some noise and so on. And our telescope is not really serving over the full sky. We're only having a tiny patch of the sky and so on and so forth. So all these kind of things, put them together will be a final test for us. And I would really like to introduce you just only the signal we are having now. And the other colleagues in the other talks will also tell you the other parts of our challenge. So currently we can have simulations to find the MOC, but we have different kind of simulations. Like the most accurate one currently we can think about was a hydrodynamic simulation, which means we simulate baryonic gas in a cosmological simulation, but even the state-of-art simulation itself is too small. We cannot really simulate a very large box so that we can put an observer in the center and see the whole sky. We cannot do that. So currently, the best we can do was using an N-body simulation, which traces the structure formation of dark matter particles, and we can model the H1 gas inside the dark matter according to the dark matter simulation, so that we can have at the same time a very large box, so that in the box in the simulation we can put an observer there, and the observer could see over all the full sky, and then he will see this kind of 21 centimeter signal. Furthermore, we can also have some kind of, for example, fast simulation modeling or direct random generation and so on. So we're using different kind of ways we can generate different types of MOCs to help us to fulfill different purpose. So 21 centimeter, let me just remind you that it's not new. It's just representing the hyperfine structure of the neutral hydrogen. So it's where 21 centimeter line signal is, we can say that we will find the neutral hydrogen or H1 gas. So on the right, you can see that in optical, there is a galaxy, but in the radio frequency, like 21 centimeter, we can see the H1 distribution of this galaxy. So exactly using the radio telescope, we can also see galaxies. And then I remember there was this question in the last talk saying, what is the advantage of BINGO or the 21 centimeter intensity mapping? Is that, for example, if we want to detect a BAO signal that we can just locate the positions and redshift of galaxies. So we want to know the 3D position of a galaxy, and then calculate the two-point correlation function of those galaxies and see and fit a correlation function with the BAO. For example, in the middle is the SSS. Every point there was a galaxy. Then the thing is that just looking at, we need a lot of galaxies positions to find the real signal. It's a statistics. So using a optical telescope, for example, we need to focus on one patch of the sky for a really long time in order to find the redshift of the galaxies. So it will take really a lot of time. But another very smart way to think about that was galaxies itself is very small, and the BAO scale itself is quite large. It's at around 100 megapascal of edge. So what about just with the cumulative way, let the signal of all galaxies accumulate together, and we only observe very roughly a very large pixel and collect all the signals from the pixels, rather than collecting every signals from every galaxy. So in that way, we can survey over the sky in much more efficient way, and that is the intensity mapping. Okay, so in one word is that we can do it much faster. So this is the mark we have built for now. For example, you can see that by watching at different frequency of the sky, that is the radio telescope can do, was essentially just watching the distribution of galaxies at different redshift. So we can watch from low redshift to high redshift. That means watching at a higher frequency to a lower frequency. The frequency represents the redshift of the galaxies, or the redshift of the neutral hydrogen. Then the question was currently, okay, we know the principle of that. We know we are trying to detect H1 gas. But on the other hand, from the simulation, from the embodied simulations we have now, we only have dark matter distribution, or more precisely say, we have the distribution of dark matter halos. And how then the problem is, what's the relation between H1 and halo? So how do we populate H1 inside halos? That is the question we want to answer. So fortunately, we have a very precise model of semi-elliptical galaxy formation. Then using the elucid simulation, it's a very highly accurate embodied simulation. Then we know where the galaxies already form and the information about the hydrogen gas. And we know that they will populate inside the galaxies, which was the central galaxies. Every dark matter halo only have one central galaxy, or it can also populate inside the satellite galaxies. In every halo, it could be multiple satellite galaxies. Then, according to the galaxy formation modeling we have done here, so we know that how much H1 gas was inside the central galaxy, shown on the left, or how much was that in a satellite galaxy, shown on the right. You can see they have very distinct behaviors. So then, in a whole dark matter halo, we don't really care too much about the distribution of the H1 gas inside the halo, but we are more interested in how much of H1 gas was inside a halo according to the halo mass. So because a halo, we know, for example, for a very low mass halo, we usually only have one central galaxy and we don't really have satellite galaxy. So in such kind of a halo, the majority contribution of H1 gas was coming from the central galaxy. And for a more massive halo, like 10 to the 13, 10 to the 14, 10 to the 15, there will be not only one central galaxy, but many satellite galaxies. And for every satellite galaxy, they will have some H1 gas. So add them up together, we will have a blue curve on the right that shows you a relation between H1 mass and the halo mass. So, and we find that comparing that relation to the observation given by Guo Hong 2020 is actually a pretty good fit for that. And on the other hand, comparing to the observation of alpha alpha, we have the luminosity function or the H1 function. So we're counting the number of the number of galaxies that have H1 mass and counting the number of those galaxies. We find that the modeling, the galaxy formation model itself, given in the green curve, you can see compared to the red one, also fits pretty well. So we can say that currently we have a model for that. And we don't only have the model at redshift 0, so now, but we also have it at a higher redshift, for example, 0.66. We find that the redshift evolution itself, it doesn't really matter too much. It doesn't differ too much. So our bingo observation was observing redshift between redshift 0.13 to redshift 0.45. So it's exactly in between 0 and 0.66. So we can do an interpolation so that at every different redshift, we will have a H1 mass halo mass relation to populate H1 mass. So on the right-hand side is the formula you can use to populate. It's super easy to use. As long as you have a halo catalog, you have a distribution of dark matter halo, you populate H1 gas according to this formula, and then you will have the H1 distribution. And next, we need a very large box unbodied simulation. Currently, we are using what's the Horizon Rim 4. It's an unbodied simulation done in Korea. So I'm currently in Korea, so it's very simple to just use this data. It has a 3.15 gigaparsec over H box. So it's super large in the sense that if you put an observer, you imagine an observer in the center of the box. You look around, you can build a full sky to covering all bingo range. So the bingo observing range was just inside the simulation box. And it also has a decent resolution to resolve the halo mass at 2.7 times 10 to the 11 solar mass of range. So we have the halo catalog. We have our way of populate H1 gas, so we can build a MOC. So we populate H1 gas according to the distribution we have, and we know how the H1, what is the distribution of H1 density, and then we can calculate the brightness temperature, or in other words, that is the 21 centimeter strength from those neutral hydrogen, and is directly proportional to the H1 density. And we can also try to rescale the map we have built here, because maybe by just populate H1 gas inside halos is not enough. Some of the gas was actually outside the halo. It's possible, around maybe 5% of those. So we can tune the value of the total H1 gas number, or we call omega H1, to a artificial level to meet our requirements. And next, we need to smooth the brightness temperature map with a Gaussian kernel, which have a full with half maximum at 40 augmented, because this is the beam size of bingo. Bingo have this kind of resolution. So by combining these kind of things, we will have the MOC map. Now, on the other hand, we also can build the MOC using other ways of doing that. Not using the halo occupation distribution of introduced here, but we can also using abundance matching. Abundance matching is another method to build that, in the way that if we know the subhalo catalog or the galaxy catalog given by the Horizon Rim 4 simulation, we just think that in a more massive subhalo, there will be more H1 gas, as simple as that. Then comparing that to the real observed H1 mass function, we can build another MOC. So we have an HOD MOC, we also have a HAM MOC. By why we want to build MOC in a different way? Because in reality, in the real nature, we actually have no idea how H1 gas really populate inside the halos. We don't know. Just like here, we have two ways of doing that. You don't know which one is right. Maybe both of those are right, both of those are wrong. So according to our observation, can we make a distinguishment between these kind of these two things? So that also can answer using the telescope. How can we really distinguish the H1 distribution there? So here is the method we can build. On the left-hand side was abundance matching. On the right-hand side was occupation distribution. And now you will have a map there. So according to the map here, we have a different method of doing that. So you will find that the distribution really looks different. For example, in the HOD on the left-hand side, you will see the HOD distribution looks really different from that of HAM in the middle, right? And it seems that the HAM distribution fluctuates more strongly. It's exactly what we would like to see. And statistically, we can measure what's the angular power spectrum. So measuring the fluctuation. So the angular power spectrum we have measured here for different maps, you will see the difference. So by normalize the HOD and HM walk to the same omega H1 level, the fluctuation will be proportional to this number. Then you can compare the green curve to the blue curve. You will find that the green curve is at every scale higher than the blue curve. That means they have a different bias. The bias means the H1 gas was populated in halos in a different way, and halos also didn't really trace dark matter perfectly. So such kind of an imperfect trace was called a bias. They will have a different bias number. And if you just scale them back and you compare at a very small scale on the right-hand side in the circle, you will find the linear effects. In the HAM, we have the galaxy, the subhalo distribution. So they will have the H1 distribution inside one halo. So that is called one halo term. You will have a slightly higher power spectrum than the HOD. So they will have a slight difference. And this kind of difference is we can really see by just measuring the angular power spectrum. Are these sensitive to the beam size? We can beam the wavelength, the frequency in different ways, like 10 megahertz of beam, or 5 megahertz, or 2 megahertz. So currently, you can see that the difference between HOD and HM have no really, and it's not sensitive to the frequency beam. It plays no role because we know the one halo term, the galaxy distribution in the halo on average is isotropic. So you have a different beam size, it doesn't really matter. And another thing we would like to see was a redshift space distortion, because in reality, we don't really see the three-dimensional position of a galaxy. We only have a two-dimensional position of the galaxy in the sky, and the third dimension was only the redshift. Redshift has two contributions here. One contribution was the cosmological expansion that tells us the distance of the galaxy, sure. And another one coming from peculiar velocity of the galaxy. That is very simple. The according to the velocity, right? So on the larger scale, you will see that maybe the distribution of the galaxy look like they are squashed into a sphere, from a sphere into this ellipsoid. And in the smaller scale, at the nonlinear scale, the originally spherical distribution will be enlarged or stretched at the direction toward us. That is called the Finkel-Oftgaard effect. So these two effects contribute together to the redshift space distortion. So such kind of distortion, you can see the difference here. On the left-hand side, it's a real space distribution. In the y-axis is the redshift direction, and on the right-hand side is the redshift direction. And the gray band, you can say that, okay, that is our beam we want to measure in this beam. And you can see that the structure you can see in this beam is slightly different in redshift space. That is what we can really see. And ideally on the right, on the left was the real space. They have slightly difference. And then by adding in the redshift space distortion effects, the Kaiser effect, you can see that it's is enhancement in the power spectrum, angular power spectrum at a smaller scale. And by adding in the finger of God effect, which is called the red 2 in green, you can see that the difference is quite tiny. Why is that? Because it should be there. We expect there will be a suppression at small scale, but we didn't see it. The reason is not because it doesn't really exist. It exists, that we're putting by hand, that is our model, but the market itself is too thick. We use a 10 megapascal, 10 megahertz thickness. It is too thick. So at maximum in our model, we can calculate, we find that the finger of God effect is at maximum around 10 megahertz. So this beam size itself is too thick. It covers up everything. But if we use a much thinner beam, for example, here at like a 2 megahertz beam, we play this animation again, you find the structure of the large scale structure evolution looks quite continuous, because we are really illustrating that in a more continuous way. They're in much thinner beams. They are more correlated. They are more, we can see more nonlinear effects. And so by measuring that in 10 megahertz, for example, here in red, we didn't really see anything here. But measuring that in blue, you can see a little suppression. And looking at the green one, you can really see the suppression very sensitive. So yeah, we have a thinner beam, we can see this effect. But remember, with a thinner beam also means we will have a larger noise compared to our signal, because signal is a cumulative signal. If we have 10 megahertz, we have at least 5 times more signal than the 2 megahertz beam. But the noise level is always a constant, you can say. So that means it's a trade-off. If you want to see more details by beaming that in a more detailed way, you will have more noise. If you beam it in a like 10 megahertz, you just lose some of those signal, but you will have a larger signal to noise ratio. So, and the third thing we want to consider was the smoothing. Don't forget that our bingo telescope was only detect our full width half maximum was 40 arcminutes. This is our resolution. By this kind of resolution, you will find that actually any difference at small scale, no matter what's the difference between HOD and HM at very small scale, or the finger of God effect, they just we barely can see any difference because of this kind of smoothing. But we can see the difference at larger scale. For example, the Kaiser effect, the different bias, these kind of things we can really detect. So that is also a key point of our mark. Tell you that what we can really see and what we can hardly see. And with a different telescope, maybe we can see more details. And finally, once we have the smog, you can take it as a real observation. Let's say we have a full sky, really good observation here, and we make a measurement of the power spectrum, and we have a theoretical prediction. Then we make a comparison, compare with our theoretical comparison, a theoretical calculation to our mark. That means we are comparing our model to a real observation. Then it will mean how we can finally find the cosmological parameters we are putting in. So you can find that the very noisy solid curve was the mark observation, and for the dashed line is a linear perturbation calculation, and the dotted line was a nonlinear modeling. And you will find that actually our observation was in between the nonlinear modeling and the nonlinear modeling. So that means our model here doesn't really work because of the complexity of H1 distribution. But what we know is that at different frequency, you can find that at the typical L range, at typical scale, we can still use the theoretical prediction. So that is also one purpose of our mark, to show that at every different frequency, at every different power spectrum we measure here, at what scale can we really use? At which scale our theoretical prediction can really work? Okay, finally, give a summary here. So we have built our halo occupation model here using the elusive simulation. We have our full sky mark using the Horizon Run 4 simulation. We have tested the finger of God effect, the relative space distortion, the beam size, the smoothing, so on and so forth. And finally, we are confirmed that using Bingo, this is what we are expecting to want to see. And thank you for your attention. Would like to take some more questions. Thanks.
Okay, thank you, Jaejun, for a nice presentation. So now we have time for questions. Please, if you have any question for Jaejun, you can open your microphone, or you can also type your question in the chat. We can also have questions from YouTube.
What is the level of correlations across frequencies here between those maps?
Sorry, can you ask again? I didn't.
I was wondering. Sorry, I joined late. I was wondering in these simulations, what is the level of cross correlations between frequencies of these maps?
The cross correlation between these maps. Okay, thanks for your question. The cross correlation between different frequency will also provide us some additional signal here. It's quite important, but we haven't tested it yet. Currently, we are only using the autocorrelation inside each frequency being, and the cross correlation between different frequency being has not been used currently yet, but it's also very useful. Thanks for your suggestion.
Okay, I expect that this should be small because it's mostly decorrelated, but yeah, thanks.
Yeah, thanks for your question.
Do you have any other questions? Let me check the YouTube. Yes, we don't have questions at YouTube too. Okay, so I guess we need to say thank you to our speaker. Thank you so much again, Jaejun.
Thanks, Bill.
It was really a pleasure. So now we can move to the next talk. I would like to invite our next speaker to share his screen with us, who is Professor Felipe Abdala.
Yes, can you hear me?
Yes, we are hearing very well, Felipe.
Okay.
Okay.
Can you see my screen?
Yes, I see it. It's perfect. So thank you again, Felipe, for being here and for present a seminar on our event. So Felipe is professor at University College London in UK. He's also one of the PIs of Bingo Collaboration. And today he's going to present us a seminar titled Bingo Telescope Optics and Data Products for Time Domain Simulations and Data Analysis. Felipe, thank you so much. So the word is all yours.
Thank you, João. So it's a rather long title, just to give a bit of a framework. So I will present here some of the results that we've presented in the paper 2107-01635 that's come out as well. But it's only a fraction of it. Then I will also present some of the work, which is some continuation of this, trying to fold that in with an alternative pipeline that we have in order to double check the simulations that we have in the group, and some map making techniques that there is from this pipeline. So just it's always good to remind, it's been said many times yesterday and today that this work relies heavily on a lot of the students, and I put here the names of the people who contributed to here on the bottom, who contributed to this paper, with honorable mentions to Alessandro, Rafael, and Pablo, who've been crucial in doing this work. And some of the follow-up work that is based on this alternative pipeline, hide and seek, and some of the modeling of this beam is being done by the people highlighted here, Karin, João, and Carlos, who barely starting their MSc and PhDs, but also Alessandro and Bruno. Okay, so to structure this, to try to make some sense out of what I'm going to talk, I will go very briefly. This is the outline of what I will present. I will go very briefly over the cosmological reference, which Bean has very kindly given a very nice talk already. So I'll skim through very quickly of it and outline the requirements that this cosmological relevance would have to a radio telescope. And then I will go through the optics and some of the results in the paper that's been submitted and put on arXiv, which is the second item here. And then I will link to some of the results of this item to the beam simulations and modeling that we have. So how well, or what simulations we're doing, and how well we eventually would like to need to know the beam, which is one of the crucial key aspects of doing an experiment like this. It was very important for all the previous CMB experiments, WMAP, Planck, and so forth, to be able to characterize the beam and to what level we'll need to characterize it, and then show some of the current results on the TOD simulation and map making with an alternative pipeline from the one that's already established in the group. So Beam has already told us that we're in an area where we have a lot of data from CMB and other experiments, and ideally we would like to learn more about this elusive dark energy cosmological constant that, and I won't go into very much detail, but as per Beam's talk, we know that we've learned so much about it from supernovae and also in connection with data from the cosmic microwave background. But one of the ways to improve this significantly is to use radio data, where we can detect the distribution of galaxies via radio observations. And the main idea of doing a survey like this is effectively to try to get this imprinted oscillation that is in the cosmos, these sound waves, which can work as a ruler if we know the wavelength, and they're imprinted into the distribution of the cosmic microwave background in temperature, and this has been exquisitely shown by Planck and previous CMB observations, but also has been seen to appear in galaxies, which in the optical, which has been shown by this paper Eisenstein about 15 years ago now, 16 years ago now, I believe. And using this as an alternative to supernova is the aim of this kind of projects, using this as a standard ruler and comparing this ruler now to the ruler backwards in time when it was imprinted in the cosmic microwave background would give us an idea of the growth of the speed at which the scale factor changes, effectively the speed at which our universe is growing, and therefore would give us an idea of dark energy. And why is this? Can this be done effectively in the radio with a speedier method? Is that if we look at galaxies, effectively we can effectively design an experiment which would have a beam that would cover and be able to detect many galaxies in the sky at the same time, and detect their collective imprint, i.e. delta T, which would come from this 21 centimeter radiation. And we can effectively, because of the size of these fluctuations, use really relatively large beams of the order of degree or so, which means that we can design very efficient machines in the radio that could try to detect this. So, in other words, a machine in the radio could be more efficient, but at the same time, these optical surveys have been doing the experiment for a long time. But a reasonably modest experiment like Bingo could try to measure this very efficiently if the right systematics are dealt with. And there's effectively a complementarity to optical data, which is because of their different systematics. In the optical, you'd have to work out what are stars, what are galaxies in this picture. For some of them, it's obvious, but for some of them, it might not be so obvious. Here, the approach to measure the single intensity with many horns has been proposed in this paper originally by Richard Batty, and then picked up and led here by the Bingo collaboration in Brazil. So, given these requirements, we effectively move on to discussing in optics that because of these scientific requirements, like I said, because of the beam size, because of the level of H1 that is in galaxies, that comes from the simulations like Jiajun has mentioned, we come up with some key specifications for a simple experiments to be feasible. And this turns out to be that you need a dish of around 40 meters with a resolution of just under a degree in frequency ranges where we can first target the lowest redshift, which is the easiest one to detect with such telescopes. And given signal to noise considerations, we need a minimum of around tens of feeds in a channel resolution of around a megahertz. So that specifies very nicely a setup that could measure these. And the setup that the Bingo collaboration eventually came up with was this setup here, which is a cross-Dragonian. And here the talk becomes a bit more technical. It becomes, so the optimal setup was a cross-Dragonian system. There are other systems considered, including the Batty et al., where there was one single dish and then a set of horns that would look at the dish from very high up. This system is more compact. Obviously, one would need to optimize the location of these horns, which is what was done in this first experiment. And here is a configuration that where we show effectively where this telescope is looking at. So counterintuitively, it's looking towards this direction. So the right rays would come, fall on this primary mirror, bounce off the secondary, and be detected by the horns here on the focal plane. The focus of the telescope is here, but we arrange the mirror in this optimal configuration for them to be optimally responsive to this cross-Dragonian system. So just for those of you who were less used to the horns, so this requires because the angle of observation of these horns towards the secondary mirror is very specific. This requires specific. So the most challenging aspect of the project is to build up the horns in a way that they have the right opening angle towards the secondary mirror, and that means that these horns for the Bingo telescope need to be very big. And this is the first. This is the model that we currently have on the table, and it was discussed yesterday. For example, alternative Chinese contributions for these horns, but this has been tested and vetted in IMP that are very good and very suitable for the project, including it being installed already. The first prototype installed as the first outrigger for the collaboration, for us to learn how this horn works by looking at the sky. So this would effectively allow us to measure the power spectrum of the 21 centimeter including these very, very modest fluctuations that appear in a very modest way because they are an imprint from other fluctuations that were the coupling between photons and electrons in the early universe. However, they are very much damped in the distribution of matter in 21 centimeter. So this optical configuration was modeled in the GRASP software, which is the state-of-the-art software for us to see the response for the system. And we obtain, so here is the effective beams that we obtain in the central focus of the telescope. So they're very nice beams, which have very low side lobes because the angle of illumination here is such that the mirror is under illuminated. So if you under illuminate a mirror, you end up reducing the amount of side lobes. So depending on the size of the horn, you can under or over illuminate the mirror and get different levels of side lobes. And this was designed so that the side lobes are kept low to as much as possible, within not losing a certain amount for signal to noise. And the optical configuration leads to a very low polarized response for these horns. Now, the thing is that these results are only at the central focus of the telescope, which is here, right? So this the whole work of this optical paper was to look at the response at other positions of the focal plane and try to optimize them in a way that this response would be as high as possible, with the polarization being as low as possible, with being a response that has as low the least amount of optical aberrations as possible. And we consider several different configurations packed in hexagonal arrays, in rectangular arrays, in shifted rectangular arrays where the horns could shift upwards and downwards in order for us to get better sampling of the focal plane, given that when this configuration is staring at the sky will rotate around the right ascension, and therefore if we can move these horns up and down in declination, we could have a better sampling of the data in the strip that we will look at. I will show you in a bit the optimal configuration. It turned out to be this one, where we had 5 shifts throughout the survey of plus or minus 15, 30, minus 15 and minus 30 centimeters of the positions of these horns. And this was done by effectively simulating the horn in every position and looking at its response. And it's not obvious by looking at this configuration here that one would have a very non-linear response to the response of the horns. But here is basically all of these graphs, they effectively show the response of these horns, so as optimizing the focal plane, which for each line here corresponds to one location of the horns in several different rows. And this was optimized in order to get the best possible configuration of this focal plane. And it was very interesting to find out that in many cases there were 2 peaks to this function, where you'd have more than one, where you'd have an optimal response and then a good response but suboptimal. And we chose the responses that were close to each other in terms of location in the Z direction, which is the placement of the horn in this location. So we end up with a configuration that a snapshot looks like this. You can see that the lowest horns here are not as efficient. The values here don't peak at 1. They're all normalized as the same. So these ones here are a bit less efficient than these, but overall they're still very efficient, still at the 90% level in terms of power, all through the focal plane chosen. And these could go up and down to be able to have better sampling as described. So with this setup, we could effectively have a machinery that gave us information about the beam in all aspects. So we could find the side lobes of the beam, even at distances very far away. Obviously, we don't want to have a very high beam far away, because a few tens of degrees away is the center of the galaxy, which we don't want to interfere with our observations. And this was presented in this paper. And also the aberrations of these beams were shown were computed, depending on whether we place the beam right at the center of the focal plane, which is this point here, or whether it's further away from the center of the focal plane. For example, I believe that these are the largest aberrations found here, and we can find out the level of the aberrations. I shouldn't really be calling this a focal plane, because it's got a funny S shape. but well, this focal surface, which was the optimal surface found. We also computed the polarized responses to this. As we'll see in a further talk, I believe by Mathieu, it's very important that the response of these is very known to polarization, given that we want to get the intensity of this 21 centimeter radiation, but the polarization could interfere with our measurements, given that you could have foregrounds leaking into the observations because of Faraday rotation, and these are decorrelated in the frequency domain, so they could be hard to remove, because a lot of the foreground removal techniques rely on correlations around the frequency axis to remove the foregrounds. And here you can see that the polarized response in U and Q is about more than 40 dB below the intensity polarization. The circular polarization, the V polarization, is somewhat higher, but we expect this to be very low from astrophysical signals anyway. So these red and orange curves here are effectively the polarized response to linear polarization of the telescope. So like I said, we simulated a survey where these horns could go up and down, and calculated also a full response when the sky passes through the whole set of beams, integrating through the right ascension. And we get these different beams for the different configurations. And we selected this orange one, which was the optimal one, which was the most stable, but also gave the highest declination strip, so the largest area in the sky. And this work actually was actually a prototype of this system to lower and raise and lower the horns was actually built in one of the partners here in Sao Paulo. That is hopefully the system that will go in the final telescope. Okay, so this is effectively the work that was presented in this paper 3, right? And then, like I said, some of the students took this simulated work and used it both for providing further beam simulations for the collaboration, but also to try to connect this with the TOD simulation tools and the map making tools. And I'll present this now. So what João, who's one of the people I presented in the beginning, who's here in the talk as well, done is that he's tried to model fitting Zernike polynomials to these beams in order to see the idea here being that we want to both have a simple fitting to the beam, something like a Gaussian fit, and I present here comparisons of the Zernike fits to the Gaussian fits, and see to what level we would need to know the beam in order to actually extract the beam information from the data appropriately. So Zernike polynomials are a very good basis to fit these beams. They usually use in optics because the way that they behave, the wavefront behaves compared to aberrations, and they're basically defined in these ways with polynomials with cosines and sines. And basically, a beam can be very easily decomposed through a set of coefficients within Zernike polynomials. And there's a very nice mathematics to it, which means that you can write these equations in form of a matrix multiplication where you have the Zernike polynomials here evaluated at the points where you know the beam, with a set of coefficients here, with a full beam here being set. So this can be done, this can be measured, this set of Zernike coefficients can be measured from either simulation like GRASP, or if at some point we have real data to fit these, this can be used directly from the real data. So the same formalism can be used from the real data. And this is done very easily. So we know that if this can be written in a matrix multiplication, the set of coefficients is just a set of matrix coefficients times the actual fit beam. So these coefficients are very easily calculable, and that's what has been done here, both to model and to fit the beam. Obviously, we need to worry about distortions of where we fit it. So João has done this in several coordinates, because of the GRASP beams are computed in UV coordinates, and we want ideally these fits to be produced in the final sky in theta phi coordinates. So we need to follow the conventions in order to obtain these distortions and Jacobians that are included in the data. And we not only have to worry about the Jacobians, but because these beams, if we're looking at fits outside the central, the bore site of the telescope, which is where where the optics is perfect, these beams could be shifted compared to the position where we look at them. So this set of rotations need to include a point through which you center the beam fits, which is where we will center this Zernike polynomials at, in terms of where we choose the zero of the θ1. So all of this has been computed in effectively this frame, which is a rotated Jacobian distorted frame, which is centered at where the beam of this telescope are. And their fits, here is just in case most people do ask regarding these fits, how these are normalized and calculated. So the way that GRASP does this normalization is that it's normalized the beam to a total power, which is integrated to 4 pi throughout the sky. So if these dBs are higher than a given value, that means how much effective magnification you have compared to isotropic radiation. And the values that João quoted here in the results are these. So they're comparisons of the power of the reconstructed beam compared to the power of the simulated beam. Now, just a note here, this value here, if the beam is fit above, this could technically go a bit above 100%, although this can't go below 100% because this is the power of the residuals divided by the power of the beams. And he computed the residual mean error pixel-wise on these fits. So these are the kind of fits that he obtained. So there's some side lobes, and here is for a given pixelization, the reconstructions that he has. Just to keep in mind, these reconstructions are reconstruct about 97–98% of the beam at these resolutions. And what we get in the end is a very nice set of 5, 10, 15 coefficients that fully describe this shape, with those residuals being at this level here. So what is nice about this is that this 15 coefficients, they can be fit for every frequency. And with one file, you can basically have the whole picture of your multi-resolution and multi-frequency beam, which has mainly the zero coefficient for the Zernike activated, but there are some other anisotropic coefficients activated. And João has done that for the beams in the focal plane. Now we've tried to improve this fit, right, by looking at the radius at which this is fit, and also the different beta parameters and different number of coefficients for the Zernike fits. So this initial fits came out at 97%, and we 97-98%, and we found out that they were reliable to about 0.3 radians, which is a few of the side lobes of the beam. But we also realized that if we improve the resolution of the actual underlying beam, this fits can actually be reliable to below 1%. And here is with an improved resolution, the beams here, they basically reconstruct 99.357% of the beam. And these are nice because they can be done, like I said, right at the center of the focal plane. And they can be done for a beam which is off axis. So this is one of the more anisotropic beams that for which João has also calculated the coefficients, which is basically reconstructed to, again, below 1% in the coefficients. Now, what we've done as well is that we've compared this to Gaussian fits, which are excellent fits for the core of the telescope, for the core of the response for the telescope. So the main lobe here on the electric field data is very well described by a Gaussian, which can be shown here. So the residuals here, if we only fit this core center of the Gaussian, they give a certain fit, which is to within a few percent again of the actual response of the telescope. This fits give us the sigma and the. Oops. Oh, thank you. So this fits gives you the size of the fits, but we also can compare them now with the actual with actual fits for a less well-behaved beam, which is here, for which the residual starts getting a bit worse. So you can see here that the fits for a non-symmetric beam can be the residuals can come up to about 30 dB, which is about 15 to 20 dB below the beam. So an error of quite a few percent. So what João has done is that he has calculated the error depending on the size of the beam with a Gaussian fit compared to the actual full beam, which for the central core here turns out to be within 1 or 2% of the actual value. But the Gaussian beam loses a few percent, and this is what's shown in this plot here. So when we get to 2 or 3 side lobes, there is a loss of power of about a few percent, which doesn't happen with the full Zernike fit. So one of the ideas of this project is to see if we will effectively need to model this first or second side lobe in order to get a good hand on the beam. And I believe that here we have at least the beam machinery to do it, given João's work. And here the idea is to present how to link these results, which could be given to the other pipeline, which has been developed in Manchester, which is fully functional in the collaboration, but to link it to this secondary pipeline that we also want to use to confirm the data. So I'll give here a few in the last 10 minutes that I have, a bit of an outline of the results for this hide and seek pipeline, which were originally developed in Zurich, and the person who originally developed them is no longer maintaining them. But because of our original connection to Zurich being our partners, we decided to use this pipeline. And it's both, the hide part is basically a data emulator that simulates time TODs, and the seek is basically an imaging pipeline from this time domain. So it's a map making tool, effectively. In this pipeline, we can have many steps that currently we set to 0 or to 1. We can apply and remove gains, backgrounds, and RFI. All of these steps have been set to 1 in the results that I will show you. But effectively, this pipeline has been used to simulate TODs with Bingo, and also to extract these TODs to produce some maps. So this pipeline has a lot of results and tools that have been designed for the Blaine Observatory, which is a facility that is available to the ETH crowd. And most of the work here that was started by Lucas Olivari and then continued by João and Carlos and Bruno has been to effectively adapt it to Bingo, to the setup of Bingo that has multiple horns, and where the map making would have to be done and then combine at the end. And we've done that to the extent that I'll show here, but we envisage to make further changes. So here's just an image of what a TOD would look like. Here on the top is by setting some gains to be variable, to be corrected. But like I said, in this simulations, we set all the gains to be equal to 1 and the background to be equal to 0. So we have effectively just a real response, like the calibrated, what we expect to be the calibrated response for the TODs. And this have been simulated from a strip here from the foregrounds. And here's just to visually see what the foregrounds would look in the TOD domain, including the temperature and what the cosmological signal would look like in this TOD domain. So what we've done is that we've simulated these with the several different horn locations for Bingo, including these arrangements going up and down, right? And these TODs, they've been therefore produced for all these 28 horns in these 5 different locations of the sky. So all the maps that I will show, effectively they simulated, it will be on the slides how many days, but given that for some of them we just simulated with 0 noise to check the map making techniques, basically they were simulated only 5 days of data for each one of the different locations of the sky. So there's a big logistic process here that the students had to go through to both simulate the TODs from these scans, and then to use the different tools available in this software to produce the maps. Now here, the algorithm has effectively 3 different currently implemented map making techniques. One which is what's called a naive map making, where you just take the center of the beam and put this value in the pixel. A second of them is that you take the beam and you effectively do an average signal in of the TOD in each one of the Hill pixels of the map, which effectively is very similar to a maximum likelihood, where you don't take the error into account. So it's an averaging map, which is the one that was readily available in the software that we decided to use. And there's also a filter mapping that allows you to impose sigma cuts and smoothing within this time domain. So in the configuration, because we haven't done any extensive tests on this filter map yet, we haven't tried to remove any fluctuations along the time, but in principle this filter map would be able to do this. So for the purpose of what I'll show here, this filter map should be very similar to the simple map, and they would only different if we start adding and attempting to remove things like 1/f noise and so forth, but or other kinds of residuals from RFI or so forth. But we've shown the results here just for completeness as well. So we made a simulation where the students chose to take only the anomalous emission from the microwave background, because it had a lot of visual things that one could try to compare the results with. And these are the results. Basically, if we do this naive mapping, which we know should be very, very bad, this is basically the results that the naive map gives by taking the center of the pixel. We know that this is substandard. And this is the results that you get. You get these holes, especially if you don't choose a pixel size which is adapted to the scanning strategy and the holes that are in the survey. But the other two techniques, the simple map and the Sigma map, give this are the results that can be compared to the original. And I think that even without doing extensive changes to this technique, the maps here look much nicer, and I think can probably be analyzed and tested to compare to the other maps that we were producing the collaboration in Italy with the Manchester pipeline to compare how these fare. And here is the simple mapper from SEEK and the Gaussian mapper from SEEK. So it's yes, this is probably my 2 minutes talk. Yes, I'm basically finished. So basically, these have been run on the data with the beams, and we also produced some noise realizations with this, including 1/f noise. These realizations have been mapped with 1/f noise. That is basically the stage at which we can interact with the rest of the collaboration to use these maps and compare to the other pipelines in existence. So I'll just leave here with the aims of what these projects have done and the next steps. Basically, we have a tool to produce these optical beams, and the idea here is to include these Zernike beams into this imaging pipeline that is in hide and seek, to be able to assess the knowledge of that we need for the beams. And there's several outstanding steps here, including checking the noise levels, comparing with other pipelines in the collaboration, and sharing this data products. So I'll leave here. This is the status of this part of the project. I'll leave here for questions if anyone has. Thanks a lot. Sorry for overrunning a bit, Ron.
Oh, absolutely, Felipe. Thank you. I'm so sorry if I disturb you.
No, that's okay. You should.
But it was amazing presentation. So, well, as we are a little bit running out of time, I will left the questions for Felipe for the break time. Maybe we can chat a little bit in the break time and discuss a little bit more this interesting results. So thank you so much, Felipe. Hope you understand. It was a pleasure to have you here.
Not a problem. Sorry. Thanks.
Okay. So now I'd like to invite our next speaker to share his presentation with us, who is André Costa. So André, thank you so much for being here. André is professor at the Center of Gravitational Cosmology at Yangzhou University in China. He's also a member of Stage 1 of Bingo Project, and he's going to present today a seminar titled Proving the Late Time Cosmic Acceleration with Bingo. So André, thank you so much. Please, the word is yours.
Thank you, John. Can you see my screen?
Yes, it's perfect.
Okay. So thank you all. So basically, my talk will be based in one of the 7 series of papers that were just submitted to arXiv and have already been submitted to ANA. So as you must all be already familiar, I mean, we have a very nice picture of what we believe is the history of the universe according to the Big Bang model. So this is a very nice picture, but we still have several processes that are still unknown, several things that we do not comprehend. And in particular, what is causing this late time cosmic acceleration that we generally call it as dark energy, but in fact, we don't really know what's happening, if it is a cosmological constant, or if we have modifications in general relativity, or if something else is causing this. So, and in cosmology, different from other sciences, we cannot reproduce our experiments freely. So the problem in cosmology is that we just have one universe. And because of this, in order to improve our constraints, we should combine different set of experiments like supernova, BO, the growth of structures in the universe, and combine all those data together, we can then have a better understanding of what's going on and what should be the preferred cosmological parameters. So different data set, they will provide us additional information because they also can have different degeneracy, and we can break the degeneracy between them when we combine those data. And also they can help us to solve tensions because different data then can be subject to different systematics. And in particular, we all are familiar with this chart of what we believe is what we observe is the content of the universe nowadays. So we have a majority of the energy budget in the universe is composed in this dark energy and dark matter that we are still trying to understand what they are. And the matter that we really observe, the baryonic matter, is about 4% of the content of the universe. And of this matter, about 76%, 75% is composed of hydrogen. So because the majority of the matter today is composed of hydrogen, it would be good to use it as a tracer of the underlying matter field in the universe. And in particular, we can do this using this 21 centimeter line that comes from neutral hydrogen. So in the neutral hydrogen, you can have the proton and electron, and they can have the spins, they can be parallel or unparallel. And if you have a shift in these orientations, you can have an emission or an absorption of a photon with 21 centimeter line. And this is what we are trying to observe in particular with this Bingo telescope. And there are basically 3 different processes that can cause this shift during the history of the universe, which is related with the coupling of the electron in those atoms with the CMB photons. We can also have this coupling and scattering with high energetic Lima alpha photons. And when the electron is excited to the high level, when it goes back, it can come with a different spin orientation than it was before. So this can also cause this emission of or absorption of 20% photons. Or we can also have these collisions between neutral hydrogen, and this can also cause this this kind of emission. And here you can see this history through the history of our universe evolution. So basically, if you have this spin temperature, which is measuring the amount of electrons that are excited or in the ground state of this hyperthin structure, if this spin temperature is higher than the CMB photon, you can have an emission of 20 centimeter line. And if they are smaller, you will have an absorption of 20 centimeter line. And after the CMB, when the redshift was about 200 or 150 more or less, you can start to observe this kind of line, this kind of phenomena. So we can have a picture of the universe since redshift of 200 up to now using this kind of observations. And depending on the epoch of the universe, you can have different mechanisms contributing to this line, coming from these Lima alpha photons, or coming from this interaction with CMB photons, or through these interactions between these neutral hydrogen. And then in different epochs, you can have an absorption, like in these dark ages, also in these when the heating begins. And during the reionization, you start to have emission of 21 centimeter photons. And because the universe, after reionization, it starts to have less and less amounts of neutral hydrogen, the global signal that you expect to observe should be going to zero, but we can still observe this very faint signal, in particular using these correlations between them and doing these 2-point correlations functions to study the structure of the universe. So then because of this 21 centimeter line allow us to probe a very large fraction of the universe's history. So we can observe the universe and probe the evolution of the structures in the universe since after the CMB at a redshift of about 200 up to now using this line. And this is a very hot topic today, and several different experiments are being built in or designed to probe this line at different epochs using different techniques, depend on the time and depending on the purpose that they are to use this line to put constraints in our cosmological models. So in particular, Bingo is one of those. And one of the techniques that we can use, as has been already said previously by several of the speakers, is using this intense mapping technique, that instead of trying to observe the amount of photons that is coming from one specific galaxy or one specific region, we can collect the total signal coming from a large fraction of the sky containing a large amount of galaxies, and using these fluctuations in this brightness temperature to understand how these structures are evolving, and for instance, use it to measure for the BO. So here you can see a picture of what this should be look like. So you have all these structures in the universe, all these galaxies distributed there, and inside, for instance, one of those galaxies, we have those clouds of neutral hydrogen that they were very dense and they were able to survive the reionization process. And those clouds, they will be emitting these 20 centimeter photons. And because of the expansion of the universe, this 20 centimeter line will actually be redshifted. And you can have this intense mapping of the universe. You will not be able to observe each one of those galaxies, but a general structure of how they are distributed in the sky. And you can do this kind of tomographic analysis of the universe history, where you have different maps at different redshifts, and you can use all of them and cross-correlating them in order to extract information about how these structures are evolving. So because of the similarities that this has with the CMB map and CMB data, we can use a similar technique and calculate and expand in this brightness temperature in spherical harmonics. And the difference here is that when you calculate this for the CMB, you just have the data from one map at one specific redshift. Your signal is at one specific redshift, but because this 20 centimeter data is coming from a 3D volume, you actually have these several maps at several different redshifts. And then because of this brightness temperature should be a function of redshift, but you do a similar analysis and you can calculate the contributions that is coming from different contributions that affect this total brightness temperature. And the more important ones are the density and the redshift space distortions that coming from the distributions of those clouds of neutral hydrogen. And we can calculate this angular cross spectra similar to what we done for the CMB analysis. So this is what we are doing. And in particular, inside the signal, we will have this information from baryon acoustic oscillations. So as Professor Binwan and also Professor Philippe said before, we have this BO that is coming from this since the beginning of the universe at early times when you have this plasma of photons and baryons. They were coupled together, and they will imprint a preferable size for the locations of galaxies later on in the universe. And we can see this, for instance, in this short move here. So at the beginning, we have some overdensed in fluctuations, and these will spread as an acoustic wave. And if you remember that actually this is happening at several different points in the space-time, so we have all these waves at different positions through the universe, and they will provide a specific position where the galaxies should be located later on. So we can populate these rings with the galaxies now. So each one of those dots should be one galaxy, and you can see all of them together. And you can clearly see here that, of course, this is an optimistic view of all of this, but you can see that there are some preferable positions, and we can then calculate the distances between them and counting the amount of the correlations between all those different positions, and counting them, we can have a statistical view of what is the size of this preferable position. And this is what we can see here. So when we combine all these different measurements, you will see that there is a small bump here at a specific position, which is about 150 megaparsec in comoving coordinates. And this peak can be used as a standard ruler to probe dark energy. So you can see here, for instance, this peak from this data in 2005 using an optical telescope, and you can see the data and also how the models can be compared with the data if you vary the amount of matter in the universe. And this is using the correlations in positions, but if we calculate actually this angular Pauly spectrum that we were discussing before, this peak will be translated into these wiggles. And now they have the same information as before, but now they will not be just one peak, but we have these different wiggles because we are transforming through this for this real space to this Fourier space. And here we have this angular Pauly spectrum at two different redshifts, which are the redshifts related with the edges of the bingo experiment. So at redshift is 0.13 and 0.45. You can also see how this BO will change as you change the redshift in your angular Pauly spectrum. So then this is what bingo is mainly trying to do. So this is the main purpose of the bingo telescope, is to measure those BO. And as have already been said, it's the idea of bingo is to be a simple telescope, and it will have a derivative scan of the universe with a stripe of the order of 15 degrees in the sky. And you can see here some of the parameters, and I just want to call your attention to some of them, which are the frequency range that we expect to observe, which comes from 908 megahertz up to 1206. So this is the redshift from redshift 0.13 to redshift 0.45. The resolution of the experiment, which is 0.67 degrees, and the total survey area in the sky, which is a bit about a little bit more than 5,000 square degrees. So this is the coverage that more or less the coverage that we will have in the sky. Now the range should be a little bit. I mean the range should be the same, but as Professor Filippo was saying before, we have a smooth survey now using this new design for the telescope, but we have this stripe with about 15 degrees in the sky. This This is the stripe that Bingo should be surveying. And this is the redshift range where Bingo should be located. So this, of course, is not the real data yet. I mean, just putting here a star just to show you what should be the redshift for Bingo, not where the real position should be, because with this, nobody knows, right? But as you can see in this picture, we are showing how the rate of change of this, what is the rate of change in the scale factor of the universe. And you can see that as we go to higher redshifts, the universe is decelerating, and you have this data from Lima alpha BAOs. We also have these BAOs using quasars, and you can see that they are consistent with this universe that is decelerating. And at redshift of about 0.6, the universe starts to accelerate, and then you can see that the rate of change in the scale factor is starting to increase. And in particular, Bingo will be measuring if we combine all the data from Bingo into just one single point. This is where Bingo should be located, and then we will be probing the universe when the universe is already in this late time acceleration phase. So what we have done in this paper 7 was to start what are the expected constraints that we will have from Bingo. So in this paper, we have considered the efficient matrix analysis, which is the optimal scenario that we expect. So basically, the idea here is to see if we change the cosmological parameters, how the signal will change. And then, given that we know what is the noise that we expect from the experiment, what should be the constraints in the cosmological parameters. So this is what we are doing. And because we have these different redshift pings, we have these correlations also between these different CLs, these different angular power spectrum at different redshifts. So this is, in this picture here, you can see what is the expected amount of noise. So you can see that at very large scales, at low mood poles, the signal is mainly contaminated by the cosmic variance. And at small scales, at large mood poles, we are, the thermal noise is dominating the total signal that we observe. So the preferred region for the Bingo signal where we expect to have the constraints from the experiment is more or less using this data from mood poles 5th up to 200. So depend on the redshift beam that you are, this thermal noise can be higher or smaller. So, but this is more or less the region where we should be. I should also note here that actually I am considering here this total sky area of about 3,000 square degrees, but using this optical set that Professor Philippe was saying before, that you can change this horn and make them shift a little bit higher and a little bit lower. This sky coverage, excluding this galactic mass, can be of the order of 4,000 square degrees. So we can even improve these results for about 30%, just considering this kind of effect. So, and then in this paper, we consider several different situations. I will not show here all the details in that analysis, because there we also considered what should be the effect if you change the total observational time of Bingo, if you have or not information from redshift space distortion, if you include or not the information from cross correlations between different redshift beams. So in the paper, you can see more information that I will show here, but here I will just focus in some late time cosmological models and what Bingo can say about them. So in particular, this is a WCD model where dark energy is modeled as a fluid with an equation of state which is constant, but we are letting this constant to be a free parameter. So it can vary and we are trying to see what's the size of the constraints that we can put from Bingo. So you can see here in this slide that just considering Bingo alone, you can already put better constraints than Planck for this equation of state of dark energy. So we have a constraint of the order of 70%. And if you combine Bingo with Planck, we can have a constraint for the equation of state of dark energy of the order of 3%. And also for this, for the Hubble constant, you can see that combine Bingo with Planck, you can have a precision in your measurement of the order of 1%. And you can also see here in this table that when you include the information from Bingo together with Planck, you have an improvement in your constraints compared with Planck alone of the order of 9% for these two parameters, for the equation of state of dark energy and for the Hubble parameter. Another scenario that we considered there was that this equation of state of dark energy is not a simply constant, but it can also evolve with redshift, use this simple parameterization, which is called this CPL parameterization. So the equation of state of dark energy has this linear dependence with the scale factor. And you can see that because we have now this additional parameter, and also because the redshift range of Bingo is narrow, we don't have a very broad redshift range. So you can see that the constraints, they become worse than before, but we still can have a constraint of the order of 3% for the Hubble parameter. And this gives us an improvement of the order of 8% with respect to Planck alone. And also we have an improvement of the order of 30% for the parameters describe the equation of state of dark energy, which are those W0 and WA. We also compared our results with SKA, so in particular with two modes of SKA using intensity mapping. Of course, we were not expecting to have better results than SKA with Bingo because SKA has a very larger area in the sky, the larger redshift range, smaller noise, and so on. But we are working with Bingo as a pathfinder for the SKA, and you can see here in this in this plot that for Bingo, for instance, can give us very good information about this neutral hydrogen, the bias for this neutral hydrogen, for instance. So you have a constraints of the order of 2.4% with Bingo plus Planck, while if you are considering this information just from SKA with Planck, the constraints is of the order of 1%. So the Bingo can already give us good information about this. We also considered the effect of including more information or complicating the information about how this neutral hydrogen is distributed in the sky. So for instance, in all the previous results, I was considering that I just had a constant bias and that the amount of neutral hydrogen was fixed in the Bingo range. But we also considered what should be the consequence if we have, if we allow this, the amount of neutral hydrogen to change, or also if we allow this bias and the amount of neutral hydrogen to change with redshift. So we considered all these scenarios, and you can see that the results, they were a little bit degraded because of the degeneracies of those parameters with the other cosmological parameters, but we can still have good results compared with the results before. And also in the worst case, we can have a constraint for the bias of the order of 9%. So after this, we also consider some models beyond the standard lambdas, beyond the standard model for dark energy, considering this just as a fluid with some equation of state. And in particular, we consider this, we can consider that we have some alternative model for gravity. And in particular here, we can parameterize this modification to gravity as a change in the Poisson equation and also change in the relation between those gravitational potentials phi and psi. And in particular, in this paper, we considered this B0 parametrization of f over gravity. And in this parametrization, we just have one parameter, this B0, which is related with the modification of gravity. And what you can see here in this picture is that Bingo cannot give good constraints or as good constraints as Planck for the H0 parameter in this model, because in this scenario here, we are considering that the background is just lambda CDM, and Planck can give very good constraints for the lambda CDM model. But on the other hand, the constraints for this B0 parameter are much better for Bingo than with Planck. And if we actually combine these two surveys together, you can have a very good estimate for both of them, for this H0 and for this B0 parameter. And this is how Bingo can help improving the constraints on this kind of scenario by breaking the degeneracies in the parameter space. And we also considered this other kind of model where you can have this interaction between dark energy and dark matter. So here we are considering a phenomenological model where both dark energy and dark matter, they are modeled as a fluid, and you can have a change of energy between them given by this Q. And because of this flow of energy between them, so this will change their evolution. And we try to put constraints in those models. And you can see that we also have a similar behavior as we had before for this modified gravity model for that B0 parametrization, where we can have, in this case here, Planck can give better constraints for the parameter psi, which is related for the interaction itself, but Bingo can give much better constraints for the equation of state of dark energy, and combine both of them together, you can have a better estimation for both of them. And this happens because this kind of model where you have this interaction between dark energy and dark matter, as far as you go in the past, the interaction will make this dark energy change and then this dark matter evolution change from what we have in the lambda CDM model, and this will give a very large imprint in the CMB results, for instance. So this is why the CMB can give better results for the interaction parameter, but on the other hand, Bingo can give better results for this equation of state, and combine them, we can break those, we can have a better constraints in the parameter space. So I will just finish here. So just to finalize, I just want to say that this was the first paper that we have about this forecast, this official forecast for the Bingo collaboration. But this is now being updated from several of our members. So we have now some works trying to go beyond this Fisher matrix analysis and actually do an MC-MC analysis. We are also improving the noise models that we are including in this analysis, including the effects of foregrounds, the effect of 1/f noise, and also in the future, we intend to include all these other contaminants that should be coming from this complete pipeline that we are working with. So I think that I will stop here. So thank you very much. And if you have any question, I am here.
Okay, thank you, André, for your nice presentation. Thank you so much for being here with us. So now we are going to have a break up to the next talk, which starts like in 30 minutes. But we can have a discussion with André and Felipe about their presentations. We can have some questions now, I guess. If you want to discuss during this break time, it's open to questions for Felipe and André. So please address your question and we can chat here.
Can we say something about the stress on the value of H0 which stands between supernova and Planck?
This result here. Well, actually, if we look here in these results that we have for instance, if we look at these results for this model, this WCDM model, you can see that Planck bingo by itself, the constraint that it will give for this H naught is of the order of 0.13, right? And if we combine bingo with, if you combine bingo with Planck, you are already contaminating your result, right? Because you are actually trying to see how bingo can say if Planck is true or if the supernova data is true, right? So you should actually combine bingo with something else if you do not want to contaminate your analysis, right? But actually the error bar that you should be expecting here just from bingo, it should be a bit large. And in fact, also these results that we have here, they are also combined with Planck. So you have these error bars that we have from these other BO data. They are not just from BO itself, but also combined with some information from Planck data. So I'm not sure.
That's why I ask, can you combine with Rees et al? Is it possible to combine with Rees et al? In any sense or not?
Well, I am not sure in the final result if our result will be in concordance with the Planck result or if it will be in concordance more with the Rees result. I mean, this we have to check. But what I am expecting is that the error bar, they will be large and probably we will not be able to disentangle this information unless we can combine with other kinds of data, and combine with more and more data, we can have a better information about this. So if you look here, for instance, in this picture, I mean, putting this bingo here in 62, right? This H naught is equal to 62. But the error bar that you are expecting is of the order of 13, right? So this is small h, right? So this should be 13 in H naught. So you have an error bar of 13 here. So you should be going from just bingo, right? Without Planck. So you should be going from 62 up to 75, or actually, yeah, up to 75, and going down up to 50 something or 40 something. So the error bar should be large. But of course, you combine with Planck, so you can reduce this error bar. But I mean, they are still of the order of H or 9 in H. No, yes, H in H naught. So probably the size of this error bar, maybe they are still a bit large, maybe. But if we combine with other data sets, so maybe we can improve these kind of constraints, but then we have to go beyond just bingo and bingo plus Planck. And of course, this depends on the model that you are considering, right? So because actually here, yes, this should be, this is for lambda CDM model actually, right? So, and I'm going here considering model beyond lambda CDM, which is this omega CDM or this CPL parameterization. So if you are just considering this lambda CDM model itself, so the constraint from Planck is already, you can see that is already much better than the constraint from the supernova data, for instance. And it is also better than the constraints from BO itself.
Thanks, Andre.
You're welcome.
Does anybody has a question for Felipe? Well, I have a question, Felipe. There you showed us that that method that you are using to build those coefficients using that matrix based on those polynomials. So just to clarify, well, if you have homogeneous, let's say homogeneous being, then you were just going to have terms on the diagonal, the main diagonal of that matrix. And another point that I thought is quite interesting is that when you have anisotropic coefficients, then you have, let's say, a more well-defined signal from the beam. When the coefficients, they are linear, they have, let's say, more approximate linear behavior in the frequency, then it looks like you have some aberration. So this is quite well, at least for me, it was quite unexpected. So if you could comment a little bit more.
So, I mean, so just to show this equation here, in principle, the rho 1 and phi 1 are just the points at which you evaluate these functions here. So in principle, they're just evaluated at those positions. So I don't think that this needs to be regularly spaced. So your second question is about the coefficients itself, right?
Yes.
So can you, I didn't quite understand it. So let's see if so here, for example, the coefficients for, well, let's take one which is a better fit, right? So this one, for example. So there's the coefficients for this fit and then this fit. So what's your comments regarding the coefficients again? I didn't quite catch it.
Yeah, the comment is that, well, if we follow one of them, for instance, this yellow one here in the middle of the graphic, it goes in an isotropic way, evolving with frequency. Then you have, let's say, a more well-behaved beam when you reconstructed the beam. But then when you go to the next slide, the coefficients, they look like growing linear or more or less linear way. So you start to see these aberrations. So this was quite interesting.
So I think we understand why this is. I think I understand why this is. So here, these coefficients, they have been done with a given fixed radius, which we picked to include something like 2 or 3 side lobes. Now, the thing is that there's a difference between the lowest frequency and the highest frequency. There's a different number of side lobes that fits in here. So basically, this change here is basically to do with the fact that the side lobe is going in and out of the fit because we're truncating here. So you can actually see that the 0, 0 coefficient, which is the strongest one, which is the main Gaussian, like, it's not Gaussian because it's a cos, right? And it has a polynomial, which is first order polynomial. It's going down, whereas the other ones are going up. That just means that you have more power on the side lobes compared to the main coefficients. So this is why this happens. Oh. So you can think that this raise and this lower down is basically the side lobes getting in. This gets more smooth because the side lobes here are more smeared out because of the aberrations. So this should all be encapsulated into these numbers. But that's the reason why this happens, is because here you've got a more fuzzy, so you still have a very significant first coefficient, which is more Gaussian-like or more first order-like, which is very well fit by the first coefficients or by a Gaussian. But the question here is if we need to model the side lobes or not. And we don't know yet if this all will be needed, right? The idea is to put this in the simulation, do analysis with a Gaussian beam and with the full Zernike beam, and then to see if that creates a residual that André can measure with his tools. So that's the idea. Maybe we will only need a Gaussian fit, but right now they have this kind of errors in them on the side lobes, few percent. So I hope, did that answer your question?
Sure, thank you. Thank you so much. Okay, so I guess we need to restart the section now. So I'd like to thank you, André and Felipe, again.
I actually have a question to André regarding
Sure,
the previous
sure.
question.
We have some time, sure.
So André, I think that regarding the question about the H0, I think it would be interesting to assert two things. I don't know if this has been done in the literature, but I wonder if you can compare the error bar that one would get on H from all the BAO experiments, but excluding Planck, compared to the value of H from the low redshift Cepheids compared to the value H from Planck. Because if there is a discrepancy, then maybe it's to do with the techniques. And if you put the BAO together and the Planck separately, it has the same physics, but it does have a separate analysis and systematics than the BAO analysis.
Mm-hmm.
I don't know if this has been done before, but I think it would be easy for you to do it, right?
Yes, yes. I think that we can do it. Sure.
And possibly the error bars would be quite discrepant with the analysis, but I don't know if they would be to what level one would be able to reject the Planck discrepancy. Sorry, that was just a comment.
Yeah, yeah. Thank you.
Okay.
Nice. So thank you so much, André, Felipe, again. It was a pleasure to have you here. So I guess we may call our next speaker, which is Elisa Ferreira. So Elisa, if you could share your screen with us. Okay, thank you, Elisa. So Elisa is professor at the University of São Paulo in Brazil. She's also a postdoc at Max Planck Institute in Germany, a member of the scientific management team of Bingo representing stage 4. She's also going to present us today a seminar titled The Cosmology Science Goals of the Bingo Telescope. So Elisa, thank you so much for being here and for all your work we made together. So the word is yours. Thank you. I guess you were mute.
Sorry for that. Can you hear me now?
Yes.
Yeah.
Yes.
Thank you so much for the very kind introduction and for the chance of speaking. So today I'm going to talk to you about the cosmology science goals of the Bingo telescope. So of course, my talk has a lot of overlaps with the talks before, so I try to go really fast through the parts that have overlap because you've heard a lot about those things. But the main goal of my talk today is to talk to you about what are the science goals of Bingo? Why are we building this? What do we plan to see or what we would desire to see with Bingo? And Bingo has two main goals, two goals, given its incredible versatility of this experiment, of this telescope. We have not only our main goal, which is cosmology, but we can also have as a secondary goal, but it's not fair to say a secondary goal, but as another goal of Bingo to also research about astrophysics. Today I'm going to talk mainly about the cosmology goal, but I ask you to please see Ricardo's talk about the astrophysics goals of Bingo. We were very happy to see how good Bingo is going to be to detect fast radio bursts, which are this new and very exciting field. And we're going to be one of the only ones in the Southern Hemisphere to see that. But also we can do other sciences like pulsars and other transients and galactic and extragalactic science. So the astrophysics goals of Bingo are also very exciting, and Ricardo is going to talk to you about it later today. So I'm here today to talk about the cosmology goals, which are the main goals. And when I mean the main goal is that it was the driver for the Bingo's design and strategy. And in cosmology, our main goal, it is to measure the BAO, the low redshift BAO signal coming from 21 centimeter for the first time or one of the first experiments to measure this. So this is a big goal and it's a big run amongst telescopes, but it is very important to measure BAO with this new technique, which will be very complementary to other techniques. So I would say that maybe the main goal of Bingo, it is to measure the BAO. And why do we want to measure the BAO? Because we want to study the expansion and properties of our universe using the BAO. We can also do redshift-based distortions, as André and Jajun talked a little bit about it. I'm not going to talk too much in this talk. But today I'm mainly going to talk to you about what do we want to study with Bingo? What are our goals? What do we think we can constrain? And what do we think if we can see? And what we mainly want to study is the dark sector and also other possible cosmological models that could be an alternative to our standard cosmological model. So the main goal of Bingo is cosmology. So it's important that then we talk about what we know already from cosmology. So repeating a little bit on what Bing said and also André and Felipe. So I shouldn't talk too much about that. So we have nowadays in cosmology this very successful description of our universe, which is the Lambda CDM, which is our standard model of cosmology. This model parameterizes the evolution of the universe from very early times until today, using 6 parameters that are constrained with sub% precision. So this model is very successful. This model is very observationally successful. And it invokes, to explain all the evolution of the universe, the need for a component called dark matter that we don't know what it is made of, and to explain the accelerated expansion of the universe that we see nowadays, the late time acceleration. We have to invoke another mechanism that I'm going to generically here call dark energy, but as we will see later, it could mean many different models. So it's a very successful model observationally. However, there are many parts that are not understood. As I said, we don't know what dark matter is, which is most of the matter, is 80% of the matter that composes our universe. And we don't know what dark energy is, which is the main component, if it is a component, or it is the main driver of the accelerated expansion that we see today. So though we know quite well the parameters of the cosmological model, we don't know the nature of this. We only have a hydrodynamical description of them. We also don't know many other things. We don't know the beginning of the universe. This is not in the standard model. This is only initial condition in the standard model, and there are many theories to explain our universe. We also don't know much about everything that happened between the CMB and today. We have this time here that we call dark ages, which where we had reionization happening, the first stars forming, and all of this is still almost uncharted territory for us. And we understand a little bit better the galaxy formation age that we have later, but not at high redshifts. So not only big problems like dark matter and dark energy, we actually don't know much about. We know a lot, but we also don't know a lot about what happened in our universe. And the future is very bright. We're going to have many telescopes using different techniques, different probes to try to explore all of those mysteries that I said. This is not at all an exhaustive list of it. It's just an example of the amazing efforts that we're having to try to explain all of these many open questions that we have in cosmology. And there is also 21 centimeters. So why 21 centimeters? So we've been talking about this. We're here because of this. 21 centimeter has the advantage of not only being a new window to the observing of the universe, so it has different systematics, it's going to have additional astrophysical and cosmological information, but it's also going to map the universe in 3D across different cosmic times. So we have different techniques that can map these dark ages, and also techniques that can map the late time evolution using intensity mapping, which is where BINGO is, which is where BINGO operates. As we can see, we operate in low redshift, so we're going to mainly talk about problems of the evolution of the universe that we can see today. For example, the problem of dark energy. And how can we obtain this information? I'm going to skip really fast through this because Andrea already talked about it. So we have this hyperfilm splitting transition of the proton-electron alignment, of the spin alignment, that produces, when you have this transition, produces the 21 centimeter red line. So it emits in this frequency. And you're going to see this radiation coming to us. You're going to see the redshift, so we can imply what happened in the universe during this time. Why can we use this, this transition? It is highly forbidden, so it's really rare. And it has a long half-life, so this is going to not change throughout the age of the universe. If it's such a rare transition, how can we study it? The advantage is that hydrogen is everywhere in the universe. And for this reason, although it's very rare, we can see this transition coming from galaxies. And the hydrogen is going to be a biased traces of our dark matter. So we're going to learn about the distribution of dark matter and also about the evolution of the universe from the time this was emitted into us. Andrea explained quite well what the processes that happen for the 21 centimeter. So all I'm going to say is that we're interested, what we measure today is the brightness temperature. And mostly we're interested in the perturbations, we're interested in the variations, these tiny perturbations in this brightness temperature, because this is going to, as a tracer of dark matter, is going to tell us about the perturbations in the density and in the dark matter of our universe. As we've been talking about this, although it's very abundant, the signal is faint from each galaxy, so we're going to use the technique of intensity mapping for BINGO. And in analogy with what we do from CMB experiments, we're going to be working with the angular power spectrum, which is shown here for what is predicted for BINGO. Okay, so this is how we're going to measure things, but how can we learn about cosmology? What can we learn? So as we said in the beginning, the main goal of BINGO is to measure the BAO, the baryon-acoustic oscillation, which are these oscillations that you have in the baryon radiation plasma, which are competition between pressure and gravity of your plasma that are going to imprint at recombination this acoustic wave, which has a size of 150 megaparsec, more or less. And this is not only imprinted in the CMB, but this is going to also be imprinted in all the galaxy distribution, like Andrea discussed. So BAO are then this statistical, because I have to really take into account all the galaxy distribution that I have to see it. It is a standard ruler because I know the size that it should be, that it was at recombination. So any difference in size today, it tells us about the expansion of the universe. So it is basically a geometrical probe of our universe. So it can be used to describe the evolution of the universe. So it tells us about the components of the universe during this period. So what we learned from BAO, from measuring BAO from cosmology, so we can measure the BAO feature, which is the Wiggles that we see in the power spectrum. And this can tell us about the Hubble parameter, which is the rate of change of our universe, and can also tell us about the angular distance, or what we cannot disentangle to two parameters is going to tell us about a quantity that involves these two. So these quantities involve cosmology, and it is because of that that we can understand the cosmology from BAO. We can also use the overall shape of the power spectrum. And by fitting different cosmologies, we can understand from the BAO, we can extract the information about the cosmology. So I'm sorry that I repeat everything. All I want you guys to think here is that we measure BAO so we can extract this information from cosmology. So let's go back to cosmology and the models. So as I said before, Lambda CDM is what we consider our standard model of cosmology. And why is this our standard model of cosmology? Is because this model is very well measured and very well, it can be described by these 6 parameters, and it's very well measured and very precise. In this model, dark matter, although we don't know what it is, the nature, we know that it is described by a collisionless cold pressureless particle. Actually, this is a hydrodynamical description, so we should say it's a fluid that has these properties. And dark energy is described by a cosmological constant that drives the cosmic acceleration that we see today, drives the accelerated expansion of our universe. And as we can see here from this combination of many different probes, which are evidences of the existence of dark energy, Lambda CDM really tells us that today, at least, the data is compatible with the cosmological constant. But what it means to have a cosmological constant. So what is dark energy? So what are we talking about? So let's go back to the Einstein's equation. So this side tells us about the geometry or how the universe expands. And this side, the energy momentum tensor, tells us about the components of the universe. If I put this in a Friedmann-Robinson-Walker universe, and in this case, I'm considering a flat Friedmann or Robinson-Walker universe, I get to the Friedmann equations that tells us that the rate of the expansion of the universe depends on each of the components of the universe. Here I put matter, radiation, and you can have other things. And the second Friedmann equation tells us the acceleration. The different components of the universe are characterized by the equation of state, which is the pressure over the density. So what I mean by having a cosmological constant, I mean adding a cosmological constant, and you can say that it is added to the right side or left side of this equation. One thing that is important is that the cosmological constant, if you write the most general Einstein's action, it should be there. So it is already a prediction of Einstein's theory of relativity. That's why people really like this solution. And as we can see here, if I have a cosmological constant, my acceleration is going to be positive here. So we have an accelerated universe. So I'm actually adding a constant to add, not adding, this constant should be there in general relativity. And this can describe the data today very well with an equation of state -1. However, although it's amazing observationally, the cosmological constant, it has many problems. So we should not just bet into the cosmological constant lightly. We should take into account all these theory problems with the cosmological constant. The most serious one are the fine-tuning problems that we have in the cosmological constant. So I observe a value of the cosmological constant that it is of this order by measuring the accelerated expansion of the universe today. But if I try to explain the cosmological constant in a quantum mechanical or in a QFT context, I have a difference in the density of many, many orders of magnitude, depending on which cutoff you take for the theory. And this wouldn't be a problem, this fine-tuning. If you just had to fine-tune this constant, maybe you have to measure it. Maybe we don't know how to control the series quite well. But actually, this fine-tuning happens in every order in perturbation theory. So you have this instability that tells you that we cannot explain this value of the cosmological constant in any sense in field theory. So although the cosmological constant is very good theoretically, is very good observationally, and is actually measured very precisely today, we should take into account that it has problems, and we maybe should consider alternatives. There is also the coincidence problem that tells us that why now? Why the cosmological constant has a value that it's only becoming important now. This might sound very special for some people. So for the reason that I said of these problems, but also for the reason that we only measure things today, we only have measures at low redshift, we have to consider other types of explanations for the cosmological constant, for the dark energy, I'm sorry, for the acceleration of late time acceleration of the universe. And there are many mechanisms that we use to explain it. So we talked about the cosmological constant. We can also add a new degree of freedom or a new component in our universe, which we also call dark energy. I'm sorry for them using the name for both. And you're basically adding something on the right side of my equation. So I'm adding another component, another fluid or another field, as you want to think, on the other side. This needs to behave exactly or very close to the cosmological constant today, but this can evolve in different ways in the future and in the past. Another way to approach to try to explain the acceleration of the universe is to modify general relativity. This modification again needs to be very close to the cosmological constant today and also not violate all that we measure from all the measurements of general relativity locally. And there are other explanations that I'm not going to say here. So it would be very interesting if not only BINGO, but the other experiments could tell us a little bit about, can we differentiate between those models? As I described the cosmological constant using the Friedmann equations, the way we should think about the dark energy degree of freedom, the extra degree of freedom, in a very general way, is that I'm adding something here on this side of the Friedmann's equation. So I'm adding a new component that has to have an equation of state smaller than -1/3, so I can have acceleration. So these models have been studied a lot in the literature. We have many, many different realizations of these models invoking very different phenomena, very different descriptions, very different parameterizations, sometimes phenomenological, sometimes fundamental. Fundamental. And sorry, I have my slides out of order. As an example, for example, we have here quintessence models, which are basically models where you add a scalar field. Here I'm simplifying, saying that you add just one scalar field or that it is a scalar field, it could be something else. And then this is going to be an extra component in your Friedmann's equation that has an equation of state smaller than -1/3, and it gives you acceleration. And you have many different models depending on the potential. You have also K-essence models, which basically means that you're changing the kinetic term of this scalar field, of this new component that you are giving. And this is going to give you an equation of state that behaves differently, and it might evolve in time. And also a different sound speed, which can tell you, it can give you maybe a different growth of structure, prediction for growth of structure. So we have this huge, zoo of models here, but it is important that we go into each and every one of them and try to see which characteristics these models might have that can help BINGO differentiate between them, and can also give very important characteristics like this K-essence models that have a very different growth of structure at z equals 0. Since we already know that it's very hard, those models are very degenerate, it's very hard to differentiate them, the predictions that they give. We used to study dark energy and any variation, any deviation from lambda CDM, we use parameterizations. So we try to parameterize deviations from lambda CDM using different parameterizations. For example, as Andrea said, we have the WCDM here, which basically it is, don't impose that we have the equation of state -1, but have the equation of state as a free parameter. Or you can have parameterizations that tell you that the equation of state is changing. Again, this can be caused by many of those models, but here we parameterize this just to ask the question, if I do I see a difference on lambda CDM? Do I see a dynamical behavior of dark energy or not? Here I cite the CPL parameterization, which is a 2 free parameter parameterization, which is basically is a very simple expansion in A, that you can see from the equation of state. So it's not valid for high Z, but it's very good for what we are doing. And this is the bingo fiducial model. And with these parameterizations, we can ask questions which avoid a little bit the degeneracy, although the degeneracy is still there, which is basically, do I see deviations from lambda? Another way to explain acceleration of the universe is to have modified gravity models. And as I said, these modified gravity models need to reproduce lambda today, and also they need to explain, to be in accordance with the local measurements of GR. Again, there are thousands of ways of modifying gravity, as we can see here in this mind map of models of modified gravity. There is an effective field theory way of describing it, where you are going to write the most general Lagrangian, in this case, the most general second order Lagrangian. And each of these terms, they are going to have one of the contributions of this modification of gravity. And each of these terms also corresponds to different models that we have in of modified gravity, and also of quintessence, because you have a relation between those models. So in this effective field way of writing is very good, because you can see basically all of the models. But again, this is very degenerate and very hard for us to really understand the difference between those models, or which of those parameters I can measure. So what we did until now, we used a parameterization also, where we parameterize any modifications of GR. And it's a very phenomenological parameterization. So basically in GR, we have Poisson's equation, and also we usually assume that we don't have an isotropic stress coming from the components. And GR doesn't have an isotropic stress coming from the geometry sector. And phi is the gravitational potential, psi is the other scalar perturbation that we have in this perturbed metric in Newtonian gauge. So in this parameterization, you modify the Poisson equation by adding this mu. So I'm basically saying that it's going to have a modification of the gravitational potential. And I also modify the equivalence that you had between these two gravitational potentials by adding this gamma factor. Again, these two are degenerate. So it is very hard to disentangle them in the data. So we usually assume a certain form for this in a way that we can describe them by only one parameter, that is B0. And this is the constraints that Andre showed in his presentation. So I think the takeaway message is the following. We are at the point that we're basically only being able, through these parameterizations, to only ask the question, do I deviate from these models, from GR or from lambda? Another possible explanation for the accelerated expansion of the universe is if the dark sector is interacting. So this might sound weird for some, but if you think in a field theory point of view, given also the small mass that the dark energy has, there is no reason why these fields are not interacting. Actually, such a light scalar field as dark energy should be interacting with almost everything. So since we don't have ways of saying that why they don't interact, imposing an interaction between them, it is theoretically fair and expected. So basically in this equation, I'm saying that they are interacting. So the energy momentum tensor of each of them or are of dark energy and dark matter doesn't conserve alone anymore. And you can see many different types of model in this really vast literature. And this list here doesn't cover even half of it, but you can have an idea. One example of this, it is a model that only exchanges energy. So here I have the continuity equation, which tells me the conservation of dark energy and dark matter. And here we can see that they don't conserve alone, they only conserve together. And they have an interaction between each other that basically tells us that one is converting into the other. This model presents very distinct characteristics, very distinct predictions that can actually be probed by Bingo and other experiments like Andres showed. And it is definitely an explanation for the accelerated expansion of our universe. So we talked mainly about dark energy and how to explain dark energy, although here we talk a little bit about dark matter. But Bingo is not only going to be good to tell us something about dark energy and about the expansion of the universe, but it's also going to be able to tell us a little bit about dark matter and answer some questions about dark matter. So one thing that we should remember ourselves is that the lambda CDM model, the CDM part of the lambda CDM model tells us that at large scales, dark matter should be a fluid, a perfect fluid that has these characteristics. It's cold, pressureless, dark, and collisionless. But the small scale data, which is not very precise, is telling us that actually we can relax these characteristics a little bit. And actually we should start asking different questions, or how cold it is, how pressureless, how small is the pressure, how small is the self-interaction. So nowadays we have been considering models of dark matter that have different characteristics than CDM. So on small scales, they might have a small interaction, they might have maybe a small interaction with baryons. And one class of these models is ultralight dark matter. Ultralight dark matter, basically, if you think about all of the models of dark matter, put this in this mass scale. Here we have primordial black holes, WIMPs. Ultralight dark matter is the lightest possible dark matter candidate that you can have. Anything lighter than that behaves like dark energy. One possible ultralight candidate are the axions, which are this explanation for dark matter that is also explanation in particle physics because it solves the strong CP problem. So axions are a very interesting explanation for dark matter, and they can also be very, very light. They can reach 10 to the minus 22 eV. But what is interesting about these models of dark matter, they behave like CDM on large scales. So if I look from far away, they behave exactly like CDM, reproducing lambda CDM. I think in 1 minute I finish. Sure. But because they have this, they behave like a wave on small scales, they have a finite Jeans length. So they suppress the formation of structures on small scales, as we can see here in the simulation, or as we can see here in the matter power spectrum, where CDM is the blue curve, but you see these suppressions. So it is known that 21 centimeter can probe these models, can probe not only the suppression of the power spectrum, but since you don't form structures on small scales, you also have a very different reionization epoch. So you're going to have an increase in the bias of hydrogen. So 21 centimeter experiments can probe the different models. So you can probe the mass and the fraction of these axions in our universe. And we even have forecasts done by this group saying that Bingo can, for example, probe this fraction with this precision. Would be also interesting to ask this question for other models of dark matter. But this is an important target. These axions can also behave like dark energy. We could also be something that we could investigate with Bingo. Last but not least, massive neutrinos. So we know that neutrinos are massive from the neutrino oscillation experiments. This would change a lot what we expect the universe to be. So depending on the mass, if it's more massive, you have more clustering. This is a simple extension of the cosmological model that should be expected. So this is something that we should always ask ourselves if we can see from Bingo. Maybe Bingo is not especially good for that, but we should ask the question if Bingo combined with other experiments cannot explain this obvious and expected extension of lambda CDM. We can also have unified models for dark matter and dark energy. So just one component to be explain both. These models have a very different clustering at low Z. So it could be that using redshift space distortions from Bingo, we can also try to test the predictions of these models. I'm going to just skip this. So to conclude, the science goals of Bingo are to measure the BAO, but using BAO and redshift space distortions, if we have, to test all these models. So it is the goal of the stage 4 working group, which is the group of theory, to ask the questions of, do I need to use those parameterizations, or can I have different models of dark energy, the ones that I showed you, or even others that have different predictions that can be measured by Bingo, or is all this too degenerate? Can I measure different models of modified gravity that have special predictions, interacting dark energy, axions, and massive neutrinos? So the answer to those questions are not obvious. Sometimes those models have very special features that make us able to probe them. And this is the role of the stage 4 group, which I'm leading, but has a lot of amazing people being part of it. But we also in stage 4 talk a little bit about astrophysics. So there are very exciting things that Bingo can see. For example, we can see pulsars, and we ask the question, can we do pulsar timing array with Bingo? Can we test the theory of having axion mini clusters that emitting radio when they are near neutron stars? Or we can even ask the questions of the origin of the FRBs. So this is the work of this working group. So different things we measure with Bingo can tell us different things about cosmology, about the dark sector, the neutrinos, modified gravity, and even things about the early universe. And you can read more in those papers that we just released. Sorry, this should be, oh, it's correct. And I leave you here with the Bingo cosmology science goals. Thank you.
Thank you so much, Elisa, for this beautiful presentation. I'm sorry if I disturbed you a little bit. Sorry.
Oh, I'm sorry.
So once we are a little bit out of time, I would ask you to make some questions for Elisa. Before the closing section, we can have time to discuss some questions with the speakers. I ask you to put your questions in the chat or in the chat at YouTube, and then we can discuss later before the closing section. Okay. So now I'm going to invite our next speaker, which is Mathieu Remazel, and I don't know if I'm pronouncing correctly, but I would like to say thank you to Mathieu for being here and take some time for our event. So Mathieu is postdoc at the University of Manchester in UK. He's also a member of stage 2 of Bingo collaboration. And today he's going to present us a seminar titled Component Separation with GNILC for 21 centimeters line intensity mapping. Mathieu, thank you so much. The word is yours.
Thank you very much. Thank you very much for the invitations, and hello everyone. So I've been asked indeed to speak about some technical aspect of component separation and foreground removal, in particular with the GNILC component separation method, which has been adopted in the analysis of bingo simulations in the several papers which have been published yesterday, actually. So just as a reminder, the goal of bingo is to perform a 21 centimeter line intensity mapping from a neutral hydrogen gas in the universe. This is the most abundant. H1 is one of the most abundant elements in the universe. And by observing the redshifted H121 line emission, which is at rest frequency of 1420 megahertz, if you observe this line emission from hydrogens at lower frequency, so this frequency range by bingo, you can perform real tomography of the large-scale structures at the different redshift slices, basically. So why do we want to do that? Because to probe dark energy, it is interesting to look for baryon-acoustic oscillations in the large-scale structure distributions across different redshifts in the low redshift universe. And one of the advantages of radio wavelengths is to allow to probe larger redshift volumes as compared to optical survey, for example. As I show in this figure on the right, bingo basically will be able to probe the distribution of matter within redshift between 0.15 up to 0.45 approximately. I have also this figure taken from a paper by Alex Wunsch and the bingo collaborations, where you can see that bingo really observe a low redshift universe as compared to other radio surveys like Tianlei and Shaimi. So the idea, as I said, is to measure especially this signal, the angular power spectrum. More generally, the 3D power spectrum, but the power spectrum of the 21 centimeter line emission from the neutral hydrogen gas in the universe at different redshift. And because this power spectrum is sensitive to baryon acoustic oscillations, and as it has been presented in previous talks, this is a powerful tracer of the geometry of the universe and the possible acceleration of the universe, and this can be used to constrain dark energy. Especially, as you see, this is sensitive to the dark energy equation of states. So the main challenge that bingo will be facing is that it will not observe directly the 21 centimeter line emission from neutral hydrogens at across redshifts. Actually, galactic foreground emission from our own Milky Way will obscure strongly the 21 centimeter signal. The emissions at redshift 0 basically today strongly obscure the cosmological signal. So we have to deal with that, and this is the purpose of this talk here. So the expected signal here observed in the bingo stripe, basically the bingo sky survey, here is shown by these two white stripes. Between these two white stripes, the temperature fluctuation of the signals are at about 0.3 milli-K in brightness temperature and religence temperature. So quite a faint signal. But obviously on top of this signal that we aim at recovering, there are astrophysical foreground emission from, for example, galactic free emissions. This is a Bremsstrahlung effect, thermal Bremsstrahlung effect from our galaxy in the ionized part of our galaxies. And you can see, if you compare with the order of magnitude of the signal, which is at about 0.3 milli-K, or let's say 3 × 10⁻⁴ Kelvin. Here you have already 3 order of magnitude above with 0.1 K for the galactic free emissions. In addition to galactic foregrounds we have also extragalactic foregrounds through extragalactic radio sources, for example, that you can see also in this map. On top of this, there is the strongest foreground emission from our galaxy, which is in the bingo frequency range of observation, is given by the galactic synchrotron emissions, which is due to cosmic ray electrons spiraling into the galactic magnetic fields of our galaxy. And here you can see it's about 5K. So basically 10 to the 4, higher amplitude compared to the cosmological signals. So this is quite challenging to subtract these foregrounds and recover the cosmological signals. And here I show also the problem in another perspective through the angular power spectrum of these maps I just showed. Here you can see on this figure that the power of the cosmological signal here is about 8 or 9 orders of magnitude below in power compared to the synchrotron emission from our galaxy or galactic free emission also. The anomalous microwave emissions is quite negligible compared to the cosmological signal in the frequency range of bingo, which is between about 960 megahertz and 1200 megahertz, basically. And so to deal with foreground contaminations, subtracting the foregrounds and extracting the cosmological signal, this is called component separations. This is very famous in CMB data analysis, for example, in the analysis of the Planck satellite. Here, for radio observation, we have similar challenge to that of CMB data concerning component separation. And the basic idea of component separation is to use frequency informations to disentangle the component of emissions, which contribute to the set of observations. So we have multi-frequency observation of the sky, and we have to combine those multi-frequency observations in a smart way in order to disentangle the various components of emissions contributing to the sky emission. Like here I show in the case of CMB data, we want to extract in particular the cosmological signal, the CMB, and disentangle it from synchrotron and thermal dust emission, etc. So this is an inverse problem in mathematics, basically. So as I said, the basic idea is to use what we know about the expected frequency dependence of the components to disentangle them and extract them. And so these component separation methods have to rely on the fact that astrophysical foregrounds and cosmological signal have distinct spectral signatures, so that multi-frequency bingo observation should allow, in principle, to disentangle the cosmological 21 centimeter signal from astrophysical foregrounds. And this figure, which are taken from the recent bingo papers, show the various spectral response of each foreground synchrotron, which is dominating over the bingo frequency range, which is highlighted by this pink stripe here. The synchrotron and free and the dominant foregrounds. The radio sources also are quite important foregrounds to 21 centimeter signal observations. CMB or spinning dust are more negligible in this radio frequency range. And here you can see the cosmological signal. So unfortunately, this is not shown in the same unit, but basically this is, as you can see here, the astrophysical foreground spectral response looks quite smooth across frequency, while the cosmological signal shows like some strong decorrelations of emissions across frequencies. So here I would like to insist on the peculiarities and the specificities of 21 centimeter component separations, which is somewhat, in fact, a bit different to CMB component separation analysis. And in particular, in contrast to CMB, where we know well the spectral signature of the CMB, which is a black body or derivative of a black body spectrum. In the case of our 21 centimeter signal, the spectral signature is unknown and somewhat random, as you can see across frequency, or I should say mostly decorrelated across frequencies. And so 21 centimeter component separation methods basically reduce to foreground subtraction techniques, because you have no spectral information about the cosmological signal you want to extract. So you just have to subtract foregrounds, and what is left from the data should be your 21 centimeter signal. So this is a bit different to component separation in CMB data analysis, where we can project on the CMB and mitigate the foregrounds. Here we really have to subtract foregrounds, and what is left should be the 21 centimeter signal. But the risk of this is by over subtracting foreground, we can lose part of the 21 centimeter signal. And this is common to any foreground subtraction technique in the context of 21 centimeter intensity mapping. So because of this non-trivial spectral signature of our 21 centimeter cosmological signal, we need to think beyond simple spectral modeling to extract the 21 centimeter signal. Component separation methods mostly rely on spectral modeling, modeling the SCD of the various components, the frequency dependence of the various components. Here we need to go a bit beyond if we hope to extract the signal. Another peculiarity of 21 centimeter signal is we often read in the literature that the foregrounds are smooth. The foreground spectral response is smooth across frequency, but this actually is a myth. For example, telescope systematics like standing waves will break this smoothness of the foregrounds. The smoothness of the spectral response will be break. So what does it mean to be smooth? What is the level of smoothness of the foreground? Even if it is tiny departure from smoothness, it can be large compared to the fluctuation of the 21 centimeter signal because of the huge discrepancy between the foregrounds and the cosmological signal. And given this huge amplitude discrepancy between foregrounds and 21 centimeter signal, any slight or any small mismodeling of the foregrounds by parametric method, for example, will result in large biases on the 21 centimeter signal. So we need to avoid making strong assumptions about foregrounds, in particular when the targeted signal, here 21 centimeter signal, is several orders of magnitude lower than the foregrounds. And finally, a third peculiarity of the 21 centimeter component separation is that as I said a bit before, the 21 centimeter signal, instead of speaking about smoothness, we should speak about decorrelations or correlation, decorrelation across frequency. The 21 centimeter signal is mostly decorrelated across frequencies, between frequencies, while astrophysical foregrounds are strongly correlated. The emission from astrophysical foregrounds is strongly correlated across frequencies. So this is what we want to exploit here. Exploit the decorrelation property of 21 centimeter with respect to foregrounds in order to discriminate between foregrounds and cosmological signal in the sky. So GENILC, which means Generalized Needlet Internal Linear Combination, is an extension of the standard blind ILC method, which has been used extensively by WMAP, Planck to produce a CMB map, for example, the ILC method. So this is an extension of the blind ILC method, which allows several things, for example, to break spectral degeneracies, like the spectral degeneracy between cosmic infrared background and galactic thermal dust emissions in CMB observations. It allows also to overcome lack of spectral information, as it is the case for the cosmological 21 centimeter line emission. And the basic property, the basic idea of GENILC is to use statistical spatial information through the Power spectrum. Sorry? No. Okay. To use statistical spatial information through the Power spectrum in order to compensate the lack of spectral information, for example, unknown SCD, spectral degeneracies, etc. It is a blind method which means no assumption.
Okay, yes, this talk aims to present the Bloom pipeline available.
Sorry, there is some background noise here, someone talking. This is a blind method, which means no assumption about astrophysical foregrounds. The sole prior assumption, again, is about the power spectrum of the cosmological signal. Cosmology is easier in some sense than astrophysics. And finally, the third point is that it is wavelet-based, which means that thanks to the property of localization of wavelets in both pixel space and harmonic space, this allows to optimize your component separations depending on the local variation of the foregrounds and the noise, both across the sky and across angular scales. So just to remind the context of GENILK, first I will show how it has been applied in the context of Planck data analysis, CMB data analysis, to give you a sense of what it means. In 2013, Planck had released the first map, all-sky map of galactic dust, thermal dust emission. The problem with this map is that it was strongly contaminated by cosmic infrared background fluctuations at small scales, which basically are background galaxies, and so different from thermal dust emissions, which come from our galaxy. And why there was this issue with the Planck data is because of a spectral degeneracy between dust and CIB. Basically, CIB and thermal dust both share similar spectral signature, a modified blackbody spectrum. And thus, by fitting a modified blackbody function to Planck data, multi-frequency data, cannot help to disentangle thermal dust and CIB emissions. GENILK goes beyond spectral modeling for component separation, as I said. Unlike other methods which rely solely on spectral information, GENILK uses statistical information, power spectrum, to discriminate dust and CIB. And so this is what I just said. While CIB and thermal dust have similar spectra, frequency spectra, they have distinct angular power spectra. So we can use this criterion to disentangle the signal. And so we use some priors, not on galactic foreground, not on galactic dust, but on the cosmological signal, the CIB, cosmic infrared background emissions, through their auto and cross power spectra, which came as a prior into GENILK. And because the statistics of the CIB is significantly different from that of galactic dust, we will be able to disentangle the two emissions. So this was the Planck 2013 map of galactic dust contaminated by CIB, and then the Planck GENILK map in 2016, which we released thanks to this GENILK method. You can see that now you are left only with the thermal dust emission of our galaxy, and the CIB emissions, fluctuations have been filtered out from the thermal dust map. And of course, the difference between these two maps give you a map of CIB fluctuation, which is also a tracer of matter, like 21 centimeter maps, a tracer of matter and dark matter. So GENILK allows to disentangle galactic dust and CIB, allows to break spectral degeneracies by going beyond just spectral modeling. Now, the GENILK method can be applied to 21 centimeter intensity mapping. As I said, we have a lack of information or a non-trivial spectral response of the cosmological 21 centimeter signal. The frequency spectrum is not trivial for 21 centimeter signal. With GENILK, we will use prior informations on the power spectrum of the cosmological signal in order to disentangle the signal from the foregrounds. And since I have been asked to speak about technical aspects, I will have a brief description of the method to give better intuitions to people who will be using this algorithm. So GENILK in 6 main steps. First, we start from the data across frequency nu, so the maps observed by BINGO, and N means the direction in the sky or the pixel. And we perform a needlet decomposition of the BINGO sky map, which means a spherical wavelet decompositions. Basically, we take the maps, perform the spherical harmonic transform. So you have the ALM coefficient of your map for all frequency bands of BINGO. And you bandpass filter through this. You bandpass filter through some needlet windows your ALM coefficients, and then you perform the inverse spherical harmonic transform to go back to a map. By doing this bandpass filtering with these various needlet windows in multiple space, in harmonic space, you in fact isolate in your map some specific range of angular scales for your fluctuations. So the first needlet bands isolate in the sky emissions only the fluctuations of at large angular scales. At higher needlet bands, or you isolate in your map the fluctuations of typical scale much smaller. And you perform component separation independently on each of this range of wavelet scales. So component separation in this way is performed locally both across the sky and across the scale, across the multiples, if you want. So the second step is that for each needlet scale, each wavelet scale, and each pixel, you compute the covariance matrix of your data for all pairs of frequency channels. The covariance matrix is just the product of your map observed at one frequency and the other map observed at the other frequency, and around some domain of pixels, around each pixels. So this is a data covariance matrix, and this is performed again for each pixel and each needlet scale. And this is an n by n matrix if you have n observation channels by bingo, like n equals 30 channels, for example. Once you have computed the data covariance matrix, now, as I said, we adopt theoretical prior on the cosmological signal. So some power spectrum of the 21 centimeter signals across the frequency channels. And we use this prior to simulate realizations of 21 centimeter signal map. These are not the actual realization in your sky. This is just other realizations based on our priors of 21 centimeter emission map. These prior maps, similarly to the data, go through the same needlet decompositions. And again, for each needlet scale and each pixel, we now compute the covariance matrix of our prior signal, 21 centimeter signal realizations. So we have two things, one data covariance matrix given by the data, and one model covariance matrix of the 21 centimeter signal obtained from our prior assumption. And we use C and S, as those two covariance matrices, to perform an eigenvalue decomposition. So just I remind that the data covariance matrix is equal to the true signal covariance matrix, 21 centimeter signal covariance matrix, plus some noise, which means noise in the general sense, foregrounds and noise. And now if we bracket on the left and on the right our data covariance matrix by our prior model covariance matrix for the signal, of course, this will look like if our prior is not so far from the reality, this will give you identity matrix on S, and this additional term, which include only the contribution for foregrounds and noise. So when you do the eigenvalue decomposition of this whitened data covariance matrix, it will look like that here. We will have identity plus some additional eigenvalue or power, which comes only from foregrounds and noise contaminations. So this eigenvalue decompositions highlights a 21 centimeter signal subspace. Those eigenvalues here do not contain any relevant power from the foregrounds because the covariance matrix, the data covariance matrix basically is consistent with identity. So it's consistent with, it means that the signal, the data here are consistent with the cosmological 21 centimeter signal. And here, the corresponding eigenvector, the subset of eigenvector here should form a basis of independent 21 centimeter modes. Here, those eigenvalues contain significant power from the foregrounds due to this additional term here. And thus, this eigenvector should form an orthonormal basis of M independent foreground modes. So this probe your foreground subspace. So in this way, we have a way to separate foregrounds and cosmological subspace. So as a highly correlated component of emissions, foregrounds can thus be decomposed on a subset of M independent templates, which is lower than the number of available channels, while the 21 centimeter signal is mostly decorrelated across frequencies. So if we discard this part of the observation space, we can recover clean 21 centimeter emissions. But we don't determine the dimension M of the foreground subspace in an ad hoc manner. We determine it with a statistical criterion, in particular the Akaike information criterion. For each needed scale in each pixel, we estimate the effective dimension M of the foreground subspace, the effective number of independent foregrounds in your sky, by minimizing the IAC criterion, which write it like that analytically for our problem here, where these mu high are just the n eigenvalue of the matrix here we have been considered. And once we have found this, this effective number of foreground components, this gives you some kind of, in fact, this gives you some kind of PCA, principal component analysis on steroids. You don't assume a specific fixed number of foreground in your sky. This is really estimated statistically, and this is varying depending on your location of the sky and depending on your scales. For largest angular scales and going to higher latitude, the effective number of foreground in your sky decreases as expected. So these are really byproduct of GenX. And once we have identified the dimension of the foreground subspace, we have the dimension of the 21 centimeter subspace, we can make a data compression, this is the last step, and perform a n minus m dimensional ILC in the 21 centimeter subspace. So this is just a weighted linear combination of the data of the bingo frequency maps with this weights matrix, which is given by these expressions, and which depends on this mixing matrix, which is just the projection into this 21 centimeter subspace with this subset of eigenvectors. So this is basically the steps. And here are some kind of results we can get. This is based on a paper by Lucas Olivari, applying GenX to sky simulations. This is a fluctuation of the 21 centimeter signal. This is for a bingo type experiment. This is a fluctuation of the 21 centimeter signal, the input in the simulations. And after foreground removal and component separation, this is a recovered map by GenX. And this is a residual, basically the difference between the recovered map and the input map. You can see that it works quite well at the map level already. Here, it is based on an independent study and official study by the Bingo collaboration based on this paper by Vincenzo. So for bingo sky simulations showing the bingo stripes, this is the input 21 centimeter signal. This is a recovered map by GenX. And these are the residual foregrounds and noise contaminations, basically the difference between these two maps. So this is quite nice and spectacular reconstruction of the 21 centimeter signal for the configuration of bingo experiment. From these maps, we can compute power spectra, angular power spectra here. This is based on another second paper of, this is just to say that this method has been applied on different simulations across the years in the literature for bingo. And this always gives quite nice results. This is another paper by Karin showing here still on bingo simulations, similar bingo simulations, the recovered power spectrum of the 21 centimeter signal. So in red, you have the power spectrum of the actual 21 centimeter signal in your simulation. And in blue, the recovered power spectrum by GenX after foreground cleaning. And the dashed line here show you the projected foreground in the recovered map, which means the residual foreground contamination for each of the foregrounds in your recovered map. And you can see that this residual foreground contamination is controlled well below the signal by GENIC. So this is quite successful again. Here I point to this paper by Lucas. So I have a chat. My time is over. I am almost done. Thanks for telling me that. So GENIC versus PCA methods in the paper of Lucas. If you PCA, if you subtract only 2 component foregrounds, you leave too many foreground contamination, too much foreground contaminations. Or if you over subtract 3 components, you also underestimate your signal, which is shown in black. And GENIC finds a sweet spot by having this dimension varying in the sky, varying in the scale. It matches perfectly the input signal, while a PCA between 2 or 3 components, you never catch the exact signal. GENIC is quite insensitive to the choice of 21 centimeter prior. Here we use a prior which is even like a smooth spectrum without any default fluctuations, let's say. Still, in green, you recover the actual power spectrum of the input signal in black. And you have some margin of error on the prior. The method is really data-driven, not prior-driven, and recover the signal. Yeah, this is my penultimate slide. Foreground subtraction versus 21 centimeter signal loss. As I said, there is a trade-off between subtracting more and more foregrounds, but without losing too much 21 centimeter signal. In this paper of the Bingo collaboration, we make this test of doing a more aggressive foreground subtraction. I mean, trying to tweak GENIC to perform less than the nominal GENIC. If you want to perform more aggressive foreground subtraction, you increase the loss of the 21 centimeter signal. If you perform less aggressive foreground subtractions to keep more signal, you leave more residuals above the expected signal, more foreground residuals. So just to say that GENIC with the IIC information criterion value of the dimension of the foreground surface MIIC actually find the sweet spot in this trade-off. And this is a takeaway, the final slide. GENIC goes beyond simple spectral modeling for component separation and 21 centimeter intensity mapping. GENIC has shown and still shows successful 21 centimeter signal reconstruction on various scale simulation of the Bingo experiment. I want to say that GENIC is not just a new tool. It has already been intensively used on real data, real Planck data. It is at the heart of several Planck collaboration papers which are there. So let us ensure successful science return from Bingo with GENIC. Thank you.
Thank you, Mathieu. Thank you very much for your nice presentation. It is really a pleasure to have you here. So I'm going to move to the next speaker, but as I told in the end of Elisa's presentation, we can have questions for you and for the other speakers in the end of the section before the closing of the event. Okay.
Sorry for having been longer than.
No, it's okay. It's all right. No problem. Thank you again, Mathieu.
Thank you.
So I'd like to invite our next speaker, who is Vincenzo Riccardo. So Vincenzo, you can share your screen with us, please.
How can I do this in the?
There's a button here in the menu bar.
I'm already the host. Okay.
Yes.
It's okay.
Yes, but we are not seeing your slides. Yeah. Now we see. Okay.
Yeah.
Okay, so let me just introduce you really quick. So Vincenzo, he's postdoc at INPE here in Brazil. He's member of the stage 2 of Bingo collaboration. And today he's going to present us a seminar titled The Bingo Telescope Simulations and Missile Assessment. So thank you so much again, Vincenzo. It's a pleasure to have you here. The word is yours.
Okay, you're welcome. Hello to everybody. So what I'm going to present in this talk is the current pipeline available to the Bingo collaboration and the main result we got with this pipeline in the last 1.5 years. Okay, this is a summary of the presentation. I will give a brief introduction of the intensity mapping pipeline. Then I'm going more in details to explain some of the modules of this mission simulator we are using mostly here at HIMPE. In particular, I will talk about the noise, how the noise is processed in the pipeline, and also the survey strategy we analyzed for the phase 1 of Bingo. Then I will talk a little bit about the component separation method we used for our analysis, in particular Junilke, and then I show the results. Okay, so the future H1 intensity mapping experiments, such as Bingo, could well be dominated by systematics and foregrounds and not by thermal noise. The systematic errors, such as gain instabilities, miscalibration, may be time dependent, which makes end-to-end simulation the only way to study how they interact with the signal of interest. The same happens for foregrounds. The only way of estimating their effect on the H1 power spectrum of the cosmological parameters is through simulations. In this sense, an end-to-end simulation pipeline for the Bingo is being developed by the collaboration. The expectation is that this pipeline will have all the steps that are needed to go from the sky to the cosmological parameter. So we can simulate sky's emission model, we can produce raw data, we can test foreground removal methods, and also the power spectrum estimation. About my work, we have used the pipeline in order to test and optimize the design of the instrument and the survey characteristics, along with the data analysis processes. The input of the pipeline is composed of maps of different emission mechanisms produced by theoretical model or by observation. We have also inherent noise of the instrument and contaminant from the environment. The number of arrangement of a horn, optical design, and the receiver characteristics are input of the pipeline, and the pipeline produces as output time series which can be turned into maps through a map-making algorithm that simulate the signal picked up by the instrument during a given period of operation. Then the output data is passed through a component separation process in order to recover the cosmological H1 component. We have considered a number of different scenarios for the Bingo. So in this figure, you can see a diagram of the Bingo simulation pipeline. In blue, you have the module which have, let me say, configurable parameters for the simulation, such as the beam shape, the number of horns, observation time, number of channels. While in red, you have the parameters that have already been measured. For example, the instrument noise module and the RFI, the radio frequency interference. Let me talk about how the sky is treated in the pipeline. So the pipeline operation makes use of a mission simulator which processes all the input information I described before, producing a time series, a TOD. The TOD is used to produce the maps at each frequency determined by the band and the size of the channel. Eventually, as a task apart from the operation of the pipeline, the set of maps produced by the simulation is processed through a component separation algorithm in order to recover the cosmological signal of interest. The sky can be described by the this equation, where you have the sky for a given frequency, a given pixel, which is the sum of the emission from the galactic foregrounds, extragalactic emission, the cosmic microwave background, and also the effect. You have also the effect of the atmosphere, and eventually you have the emission of the cosmological signal. So for the simulation, the first thing you need to simulate is the H1 emission itself. The H1 emission, a low redshift, in other words, after the re-ionization period has ended, is assumed to be confined to discrete elements such galaxies, bubbles, and filaments. And you can use this equation to calculate the mean temperature of the H1 for a given redshift, where omega is the H1 comoving mass density in terms of the current critical density. Using the H1 angular power spectrum and assuming a Gaussian statistic, we can easily produce a full sky maps of the H1 signal using the Flask software, which is already available to the Bingo collaboration. And the Flask software, we can assume a log normal distribution of the H1 signal. In this log normal case, we also use the CLS from a code developed by the University College of London, the so-called UCLCL. We use DCLs as input. I use for my simulations. The Flask, we can also make auto and cross correlation between different observers, as well as different galaxy population. Okay, what about the foregrounds? So the foregrounds, which we consider as are contaminants for our purposes, can be divided in three main types. Galactic emissions, extragalactic radio sources, and the cosmic background emission. The galactic stellar emission can be described by four components. The synchrotron emission, which arises from an energetic charged particle moving in the galactic magnetic field. The free emission, which arises from the interaction of free electrons with ions in the galactic ionized media. And the anomalous microwave emission, with the most accepted mechanism for it being the spinning dust model, in which the electric dipoles in the small dust grain spin up, producing radio emission. Extragalactic radio sources are an inhomogeneous mix of radio galaxies, quasars, and other objects. They can be divided into two populations: bright and isolated pointy sources, which can be detected by the instrument and then removed directly using the observed data, and a continuum of unresolved sources, which can only be removed by component separation. Most of the cosmic radiation that we observe today is in the form of an isotropic black-body spectrum, which is the cosmic microwave background. Cosmic microwave background temperature, however, is not perfectly homogeneous and has fluctuation of the order of 100 microkelvin. So this makes this emission a relevant foreground for intensity mapping. And so we need to use publicly available templates to remove this emission. Here I'm showing two maps, one of synchrotron and free that we used for our simulation. I generated these maps with the intensity mapping pipeline. Let me talk about a little bit about the time ordered data, the TOD. This module of the pipeline takes as an input the idealized sky maps, LPX maps, calculated by the previous module, and processes it into a TOD. To calculate the TOD, a given experimental design is assumed, for example, effective dish diameter, number of channel, the latitude, beam profile. Particularly for the beam profile, we are using for our simulation a circular Gaussian profile, which is given by this equation, where Ni0 is the central frequency of the bingo, and theta Ni0 is the full weight arc maximum of the beam at the central frequency, which for the bingo is 40 arc minutes. In addition to this, we also concerned about radio frequency interference, because radio frequency interference are emission in radio waves made by man, such as personal computers, cell phones, airplanes, and so on. This is ways to reduce the impact of RFI in intensity mapping observation is to build a telescope in a remote site, far from any large cities or infrastructure, and the RFI has a frequency response very similar to the H1 signal, which means that if this type of emission is not low enough, at least less than the thermal noise of the experiment, no component separation method will be able to remove it from the observed data. So this is a crucial step also to take into account when we make simulations. So the noise. There are two main noises we need to care about for the bingo telescope. The thermal noise, which is caused by the thermal motion of the charge carriers, and can be accurately modeled as a Gaussian white noise distribution, and the 1/f noise, which is produced by gain fluctuation of the receiver amplifiers, and is quite correlated across all frequency channels. The 1/f noise, the RMS of the thermal noise is described by this equation, where T6 is the temperature, the system temperature of the telescope. F is the sample frequency. Delta is the frequency channel beam, the width. The 1/f noise manifests itself as a large-scale spatial fluctuation in the map, and is not trivial to separate it from the cosmological signal of interest. This noise is considered as a systematic for the telescope. So, in talking about the pipeline, the 1/f noise is assumed to be a small multiplicative variation around the system temperature and is Gaussian distributed. Delta T is the contribution to the temperature given by the noise, and is equal to the variation of the gain inside the receiver amplifier, the product, and with the temperature system temperature, which is also time dependent. So the delta G can be described, the power spectral density can be described by two parts. The first part is the power spectrum of the temporal fluctuation, which is this one, which is and is characterized by the spectral index alpha. In this case is 1. This is a peak noise. And F key, where F key is the Ni frequency, which actually is the frequency where the 1/f noise, the power spectral density over the 1/f noise, crosses the white noise. The second part is describes the correlation of the noise in frequency, and may be described by a conservative power law model. Here you have the index, spectral index beta, which takes into account the correlation of the 1/f noise in the frequency channels. So as I say, the spectral index beta describes a 1/f noise identical in every receiver channel when beta is 0. So we have a perfectly correlated noise, and a noise that is independent in every channel when beta is equal to 1. This is an important parameter that we can set as an input parameter in the pipeline when we generate the noise. For an ideal receiver, also the knee frequency, which is this one in this plot, where the 1/f noise crosses the white noise, should be 0 for an ideal receiver, meaning that the receiver TOD is dominated only by flat power spectrum thermal noise. But it's not the real case, of course. So the thermal and 1/f noise are both simulated from independent noise realization. The stability of the bingo noise properties can be quantified by the variation in the white noise, in the knee frequency, and the spectral index, beta, over the lifetime of the experiment. The presence of 1/f noise in the number observation map introduces stripes parallel to the scan circle strategy, as you can see in this example map. So its main effect is to increase the uncertainty of measurement, mostly on large spatial scales. And the size of the spatial scales is set by the knee frequency. So it's very important to keep the value of the knee frequency as low as possible. This striped structure appears because the mean level of the noise is in general different for each circle of measurement. Okay, now let me talk about a little bit of the map making, how the maps are generated inside the pipeline, which uses a naive map mapping algorithm. And so the pipeline takes an observed simulated TOD in the time frequency domain as an input and processes it into an HLPX maps. In the process, it calibrates the data and automatically masks the RFI contamination. For example, TOD is masked if known bright objects, such as the sun and the moon, are too close to the telescope pointing. Furthermore, frequency bands are known to be unusable, such as bands contaminated by satellite communication or, for example, by aviation transponder. So it's important to remove, to analyze first the TOD and to remove a priori these frequency bands. For the bingo, the TOD consists of a temporal measurement in a given channel in the frequency range of bingo and for a given time of observation. In particular, we can consider we can imagine the TOD, the map as a set of pixels, and each pixel is filled with the mean value of all measurement in that pixel according to this equation of temperature. So for a given pixel, you have a temperature value, and this is the mean value of the temperature at a given time. As I said before, once we have the map, you can then pass this map through a component separation algorithm and trying to recover the H1 signal. The observational strategy. This was one of the main analysis we did using the pipeline in order to understand which was the best configuration, focal plane configuration for the bingo telescope. And the arrangement of the horns in the focal plane has been optimized in such a way to cover 15 degrees declination strip, and at the same time to have some redundancy. In other words, redundancy is when beams have some superposition with beams of adjacent horns. This will increase the signal to noise ratio. The position of each horn is defined by two parameters. The first is a Cartesian parameters, x and y, on focal plane coordinates. And then you have the elevation and the azimuth angles. Horns are located in the outermost region of the focal plane array, are slightly tilted with respect to the focal plane to under-illuminate the secondary mirror and to reduce side lobes and ground contaminations. But as you already know, the Bingo is a fixed telescope, so which uses the rotation of the Earth to scan the sky. For the Bingo phase 1 analysis, we considered two configurations for the focal plane, which are the hexagonal configuration with 31 horns and the double rectangular with 28 horns. This is actually the configuration which was chosen for the Bingo. And so with these two configurations, the sky coverage obtained when we use the resolution of NSide 128, which is roughly 27 arcminus of resolution. So when you use this resolution with this focal plane arrangement, you get gaps between data stripes in your map with unobserved regions at constant declination. One of the ways to avoid this is to change the declination coverage by varying the pointing of the full focal plane. You can do this by moving up and down after a given time of observation. For example, you can do this once per year by moving up and down all the horns in order to get a more uniform sky coverage. So changing the declination coverage can be accomplished by moving all horns vertically different steps. You are limited, you are constrained by the hexagonal housing of the horn. So the maximum interval in which you can move the horns is more or less 300 millimeters. And this is the maximum displacement. Okay, so in these two figures, we have simulated the resulting Bingo coverage after displacing all the horns up and down in the focal plane with steps of 150 millimeters. So in total are 5 different positions. After 5 years of integration, and you have generated the heat maps. Meaning, heat maps are maps showing the number of showing how many times a pixel is scanned by the horn. We did this for the central channel of Bingo. So all the maps are created with an NSide 128 and then are degraded to Bingo resolution, which is for 30 minutes. And then the 5 elevations are summed to generate this final map after 5 years. So the first you can see here is the horn repositioning strategy results in a more homogeneous covered area. We found 25% more coverage than the fixed elevation option for the hexagonal format and 12% more coverage for the double rectangular, which will allow us to obtain a more uniform signal-to-noise ratio per pixel and a better recovery of the overall H1 signal. Regarding the two arrangements, we also found differences in terms of sky coverage and uniformity. In particular, the declination strip here is 15 degrees in declination, while for the double rectangular is, as I said before, is bigger. So this will also increase the observation region. The better sky coverage uniformity achieved with the double rectangular rays is clearly visible in this plot, where you have here you can see here this plot as a section of the Bingo region. I mean, you can see here as the lowest declination, and this is the higher declination. So you have here the number of Hell peaks in the Hell peaks map, and here on the y-axis you have the number of observation per pixel. So you can see that the peaks in the hexagonal array, which is the gray one, are due to the feed redundancy along the scan direction, since we have more redundancy for the hexagonal configuration, since you have more horns looking at the same declination, constant declination. So the redundancy, which are actually our pixels seeing at the same sky patch each day, are shown in this plot by these peaks. So it's also visible, clearly visible, how different feed arrays, horns arrays, can affect uniformity in the sky coverage. So for double rectangular, you have less number of observation, but you have a more uniform coverage. It is worth noting that the noise power spectrum of an homogeneous coverage is independent of the pixel size used to produce the map. In the case of an homogeneous coverage, which is our case when we increase the resolution of the map, the noise power can be expressed by the following equation, where sigma is the noise in the map, and px is the number of pixels in your map. So the amplitude of the noise power spectrum increases when the times distribution is not uniform, compared to an uniform distribution, since you have a less number of pixels. So when the inhomogeneity is not too large, such an increase in the noise remains small. But when we have found in our analysis a noise level of 70% greater when the sky is scanned with the hexagonal horn configuration compared to the double rectangular arrangement and N-side 128. Since with the hexagonal arrangement, we got some gaps in the map with these when we use an N-side 128. So we can also improve. Reduce the error in the power spectrum using the double rectangular configuration. And another, when the gaps are bigger, for example, the noise level can reach values of 70%. In the extreme case where half of the pixels are observed 5 times more often than the other half passed. Another improvement we can get with the double rectangular configuration is that we can reach a better than Nyquist configuration. In other words, we have a number of samples per beam equal to 2, and this is very important since with a sampling better than the Nyquist, we can will allow us to use other techniques to extract further resolution map from the maps. So this was one of the reason also we opted for the double rectangular configuration. So let me give a brief introduction to the component separation. The components in radio astronomy observation describe a mixture of cosmological signal emitted in the early universe, with also astrophysical sources emitting in the late universe, such as galactic foregrounds, as extragalactic point sources. And then we have also contamination from instrumental signals, thermal and 1/f noise. So component separation is a term that refers to any data processing that try to disentangle this emission from the cosmological signal of interest. So a component separation consists in isolating in an optimal way the wanted signal from all the other components present in the data. So you can describe the component separation by modeling the data observed at a given frequency for a given pixel, where B is the where epsilon is where Y is the sky emission, N is the noise, and B depends on the instrumental beam, which generally is assumed to be Gaussian. This is a convolution between the signal and the beam, and you have to add the noise. So the sky is a superposition of emission of components, and it can be described by this linear mixture where A takes into account the frequency dependence of each component of emission of the sky, where S is a given component. So I'm not going into detail of Janilky because it was already presented before by Mathieu, who is one of the authors of this code. So let me say just that Janilky was already used for example, for Planck analysis, and the Janilky is a blind component separation method, in the sense that it does not rely on any assumption concerning astrophysical foregrounds. The only prior assumption of Janilky is about the overall shape of the cosmological H1 power spectrum. In our analysis at INPE, we have analyzed the Janilky method, and we have used this method we have applied this method for the first time to a set of end-to-end simulation generated with intensity mapping pipeline, and we have generated the simulation changing a lot of parameters, input parameters, in order to understand how these affect the reconstruction of the power spectrum with the Janilky. For the analysis, I'm going to give some details here. For the analysis, we use the Galaxy mask, which is actually being used by the entire collaboration of Bing, with a cosine approximation of 3 degrees. All the maps are generated by Inside 128, and we have compared the result obtained with the Janilky with the standard PCA method, which is commonly used in H1 intensity mapping simulation. In order to quantify the recovery performance of the Janilky, we use this index NREC, which is given by this equation, where NL is the total number of multiple, and CH is the number of channels, and CR is the recovery cell, and these are the input cells. In this table, you can see some of the parameters we have used. We have tested the Janilky. The Janilky used maps with 1 and 2 years of integration time. We have changed the number of feeds, and also we have used different spectral index of the 1/f noise to see how this can impact on the reconstruction. Here I summarized the results, some of the results obtained with the Genilchi and the PSA for using different integration time, 1 year, 2 year, 5 year for the double rectangular array with 28 horns. For comparison, we have also simulated the hexagonal array and the double rectangular with the 56 horns, since the structure of the telescope actually allow to host up to 56 horns. So maybe in future, if we have the financial resources, we can, in principle, we can update the telescope. So you can see here the reconstruction, for an ideal scenario. So this index should be equal to 0. This means that the H1 spectrum was perfectly recovered. So here you can see that the recovery increases with more integration time. But we can see too much difference when we change in terms of recovery. Of course, too much difference when we use the hexagonal or the double rectangular configuration. When you increase the number of horns, you have a small improvement, and the results are also comparable with the PSA method. About the spectra, let me introduce first the cross-correlation coefficients, which is a complementary way to measure the signal recovery sensitive to scale-dependent signal loss. Here I'm showing the recovery of the power of the H1 power spectrum in the case of a 1 year simulation with the double rectangular configuration. Number of channels was set to 30, and the beta value, which is the frequency spectral index of the 1/f noise, was set to 0.25. We use this value as our fiducial value, since this value was obtained by previous measurement at the Jodrell Bank Observatory in Manchester with a prototype of a full correlation receiver. So you can see here that the recovery of the spectrum is quite good. One of the most features of both Genilchi and PSA that they have not changed the statistics of the recovered power spectrum. And here you have the cross-correlation coefficients. For a perfect reconstruction, it should be it should be equal to 1. So you can see that this is lower, it's less than 1. This means that both the methods are underestimate the power spectrum, the H1 power spectrum, and all here at the end of the multiple interval, you have the value is bigger than 1. This means that in this case the recovered spectrum is contaminated. I mean, you are recovering the H1 spectrum, the H1 signal, plus some foregrounds. So as I said before, the component separation method does not affect significantly the wanted signal statistics, but it underestimates the power spectrum. Anyway, we can see that the two methods are comparable throughout the entire range of multiples. And while here I'm showing the performance of the Genilchi for each channel. because all the results I shown before was for the central channel of Bingo, so for 1.1 gigahertz. So you can see that the performance at the edges of the band, frequency band, are worse. This is because there is less freedom for the method to fit for the independent components of emission. So we should take into account also this problem when we are going to deal with the real data from the telescope. Here, just for comparison, I'm showing this is the Bingo region. Is a map of the Bingo region where here you have the input H1 signal generated with Flasky software. This is the galactic mask. So these two stripes are masked. This is the recovered signal, and this is the residual map. So the conclusion, what I can say is that we have carried out a study, an analysis to improve and to understand which was the best configuration for the telescope. Of course, I didn't show here all the results and on all the we got during our work. Because for time purposes, and then we have also applied for the first time the GENILC method to maps generated by the intensity mapping pipeline. The results are quite good. We are confident that we can still improve these results, and actually the best results in terms of accuracy was of 12%. When this result, we got these results when we recovered the spectrum with the map after a 5 year of integration time. So as the telescope construction proceeds, we also work on the improvement of the pipeline. We are still working on the improvement, and we are trying to in the near future we intend to include the extragalactic point radio sources in module in the simulation. We are also working on the optimization of the GENILC. In particular, team there is Eduardo that is working on this along with Mathieu and Larissa, and we have already improved the results I showed in this presentation. All the analysis carried out by Eduardo is producing a paper which we will try to submit this year. And we another issue.
Vincenzo, I guess I'm so sorry, but I guess we need to stop here. But okay, thank you so much. Thank you.
It was over. It was already over. Sorry for that.
No, there's no problem.
Okay.
I should say sorry. So thank you.
Okay.
So as I told before, we are going to have some questions for Vincenzo and the other speakers in the end of this section. So I would like to invite the next speaker to share his screen with us, who is Ricardo. So,
can you see my screen, João? It's full screen now.
Yes, now I'm seeing. So thank you so much, Ricardo, for being here today. So Ricardo is postdoc at TUM in Germany. He's also a member of the scientific management team of Bingo, representing stage 1 and he's going to present us a seminar titled Elucidating Fast Radio Bursts with the Bingo Telescope. Thank you so much, Ricardo. The time is yours.
Well, thank you very much, João, for this nice introduction and for the opportunity to talk about this work. Well, as was mentioned many times today and yesterday, the main goal of Bingo is to measure BO using the 21 centimeter line. However, Bingo can contribute to additional science, to other branches in science, for example, in astrophysics. And specifically, Bingo can help to elucidate fast radio bursts, as I'm going to mention in this talk. Well, this work is, the person interested can find more details in the first paper of the collaboration. And this work was made in collaboration with several members of Bingo, but mainly with Marcelo Santos, Amilcar Queiroz, Fred Vieira, Alex Wunsch, and Felipe Abdala. Well, now, what are the so-called fast radio bursts? Well, fast radio bursts is a relatively new phenomenon discovered in 2007 by Duncan Lorimer, this guy over here, using data from the Parkes telescope. And they were also called as Lorimer bursts. They have two main features. So they are very bright and very short. They are bursts of radio photons in different frequencies that travels from an still to be understood source to Earth. And because of this mysterious origin, they have attracted a lot of attention in the media everywhere in the world. And also because of especially in the last few years, because of the construction of new radio telescopes, such as CHIME, for example. Well, but the main question that still remains is, where do they come from? So we still don't know their origin for certain. So this is still a big issue, and Bingo maybe can help to elucidate this in the near future. So here's just a plot of the radio spectrum and the optical spectrum. So basically we have around the ultra high frequency, the television. Bingo, as it was mentioned several times, will operate in a frequency between 980 megahertz and 1260 megahertz. And fast radio bursts have been detected in a frequency range of 100 megahertz and 8 gigahertz. So Bingo lies around here, and fast radio bursts have been detected around this region over here. Also, Bingo has a very good prospect to detect it. Well, as I mentioned, fast radio bursts are very short and very bright radio waves. And in order to see that, we can see in this plot the spectral luminosity, which is basically power per frequency, and the duration of several different astrophysical phenomena. So for example, we have here pulsars, we have here stars, supernova, and gamma rays, for example, gamma ray bursts. And we see that fast radio bursts is in a very isolated place here. So they are very bright and very short in terms of duration. So they last, for example, milliseconds. So these 2 points are very, very specific features of fast radio bursts. Well, another feature, which actually is one of the things that is used to detect fast radio bursts, is a dispersion. So as all of you may know, dispersion is a phenomenon that, for example, if you take a prism from the pink light covered the dark side of the moon, we have a light ray that crosses this prism, and then it causes the light ray is dispersed, and then each wavelength will travel with a different velocity. Now, whenever fast radio bursts are produced in some galaxy, in some host galaxy, for example, far from Earth, they are produced there and they travel through the space and to Earth where they are detected. But this space is not empty, so they travel basically the intergalactic medium, which is composed by free electrons. And then these free electrons act as a prism So they basically disperse this radiation that is emitted in the source, and then photons with different frequencies will arrive on Earth at different times because they will have different velocities. In practice, this is seen in this plot over here, which is the plot of the first detected FRB in 2007. So we see here in the x-axis the observed time, and here the different frequencies that were detected. As we can see, this waterfall behavior shows that photons with higher frequencies arrive on Earth earlier than photons with lower frequencies. This is a way to detect FRBs because we can use a pipeline to see if the data has this specific behavior. And this behavior happens because the time delay, the arrival time of the photons depends on the inverse of the frequency through this mathematical relation, for example. And if we did disperse this pulse, so if we basically try to correct this and put everything aligned, we obtain this pulse, this very big pulse here, which has a duration of some milliseconds. Well, now there are a lot of science that can be done once we detect this observed time delay. As an example, I can say that the observed time delay of fast radio bursts and other astrophysical transients, for example, gamma ray bursts, can be used to constrain the weak equivalence principle, as many people have done in the past, including Orfeo Bertolami and me in the paper in 2008. It can be used also to constrain the photon mass, to put upper limits on the photon mass, to constrain Lorentz symmetry violation, and to constrain some dark matter models. Well, so far, over 100 FRBs have been detected through several different radio telescopes. From this over 100 FRBs, more or less 11 are known to be repeating. So basically, FRBs are sporadic events that can happen everywhere in the sky. But most of them, at least the detected ones, happens only once. So it's a flash and then it stops and that's it. However, around 11 of them are known to be repeaters, which means that they are not a single event, but they continuously happen during some time. And because of these detections, actually the first repeating FRB was detected in 2012, and which is this FRB 121102. And during a lot of time, this was the only known FRB to be repeater. In the last few years, CHIME and other instruments detected other repeaters. And this repeating FRB shows that not all FRBs can be from a source that has some cataclysmic event. So for example, in a supernova, the supernova explodes, a star explodes, causes a supernova, and that's this. The source kills itself. But this kind of source cannot explain the repeating FRBs because those are phenomena that happens not only once. Well, so far, only 2 FRBs are known to be periodic, which means that they are repeaters, but they have a specific period. So the first one is this FRB, which has a period of 106,757 days. And the other FRB is this one, discovered recently, which has a period of roughly 16 days. So what happens is that, for example, for this FRB, it starts shining, flashing during 4 days, and then after that, it turns off, and then remains that until the 70th day, where the cycles continues. Well, before last year, it was believed that the FRBs were purely an extragalactic phenomena because it was due to the observed time delay that I mentioned before, and it was possible to infer the dispersion measure. And this dispersion measure was very high, indicating a possible extragalactic origin. However, in the last year, an FRB was detected in our galaxy, in the Milky Way, and it came from a magnetoid, which is basically a pulsar with a very strong magnetic field. So this is just an illustration of this phenomena. And this opens a new avenues in trying to understand the origin of FRBs. However, although this FRB is for sure believed to come from this magnetosphere, this doesn't end the question where they come from, because it's known that there are a lot of magnetars in the Milky Way. However, only one magnetar was known to be as a source of FRB. And also there might be that, for example, a repeating FRB has a different source of a non-repeating FRB. So we might have two different kind of sources depending on the emission of FRB. Among several possibilities of explanations for the origin, there are mergers and interactions between compact objects, for example, mergers between neutron stars and black holes. They also may come from pulsars, white dwarfs, as remnants of supernova, or inactive galactic nuclei. Well, now we learned that BINGO is a radio telescope, so it can measure radio waves, and FRBs are basically radio waves. And then the question that we may ask is, well, can BINGO detect FRBs? The answer is yes, because we'll need only a few modifications in the software, for example, and another few details. And if so, how many FRBs BINGO can detect? Well, in order to answer this question, we'll need some ingredients, because we basically don't know a lot about FRBs. So we have to make some assumptions in order to understand, for example, how is the distribution of the luminosity of the FRBs, how they are distributed in terms of redshift, and so on. And then in order to do that, there are a lot of models in the literature that can explain some of the data, and we take some of the assumptions the models made by this recent paper. So the first ingredient is the FRB luminosity. So we can assume that the luminosity of the FRBs are given by the Schechter function. The Schechter function is a distribution that is used, for example, in galaxies or stars. And then it has this very simple behavior. So this phi prime is a normalization. The L is the luminosity. L prime is the cutoff luminosity, which basically indicates in what of those functions dominates this Schechter function. So for example, it can be dominated by the exponential term over here, or this power law term over here, depending on the size of the luminosity when compared to the cutoff luminosity. And this other parameter here, this gamma, is a power law index, and those values were taken from this work that constrained this function using for the luminosity of FRBs. Well, now in practice, what we really need to calculate the detection rate is not simply the Schechter function, but is the integral of the Schechter function from a minimal luminosity, which can be detected by our instruments, up to, in principle, an infinite luminosity. And this integral will give an incomplete gamma function, which will depend on the minimal luminosity. And then this function has this behavior plotted over here when we take these parameters, these values, and in terms of the minimal luminosity. Now, another ingredient that we'll need is how FRBs are distributed according to the redshift. So one way to see this, to use this, is consider a function that describes cosmic light volume. So this is given by this expression over here, where C, the speed of light, R of Z is the commuting distance, and this term over here is the Hubble rate, where we can use, for example, the Planck parameters to give this nice plot of this function in terms of the redshift. Now, this distribution function more or less resembles a Poisson distribution. Now we will need something to relate this minimal luminosity to something that we really detect in our telescope. And one way to reach there is using the flux density. So the flux density is basically power per area per frequency. And it may depend on the frequency to some power. This power is called the spectral index. Now, the flux density at the peak of the signal is of the produced FRB is given by this expression where DL is the luminosity distance, this bolometric function, this bolometric luminosity will be the minimal luminosity. Nu1 and Nu2 are the telescope frequencies, which is in this range for bingo, and Nu high and Nu low are the highest and lowest frequencies in which the source emits by seeing the observer. Well, now, usually we don't know what this Nu high and Nu low are, but we can make some assumptions. For example, if we think that the source emits in a bandwidth of 1 gigahertz, for example, we can take some values for Nu high and Nu low, for example, 1400 megahertz and 14 megahertz, and then we can calculate this guy over here. Later on, I'll show how this choice of frequencies change our results. Well, now the last thing that we'll need is how precisely the flux density is related to what we can observe. Now, a given telescope can observe a minimum flux density, which is basically, as the name says, is the minimum flux density given the instrument details of the telescope. So it depends of the system temperature, depends on the number of polarizations, depends on the bandwidth of the telescope, and depends on the sampling time, and also on the further gain of the telescope. Now for bingo, this minimum flux density is 0.41 Janskis, and we can see that, for example, our signal to noise ratio, which is basically the ratio between the signal to our noise, is just the ratio between the two flux densities that I showed before. Now we have basically all the ingredients that we need to calculate the bingo detection rate. Now, if we put all the ingredients together, we can obtain this nice formula, which will show how many FRBs will be detected per any specific unit of time, for example, per day, per month, so on. And it depends on several of the ingredients that I showed before. So it basically depends on the integral of the solid angle, which will give a field of view of the telescope. Depends on the cosmic volume, the integral of the cosmic volume that I showed before, integrated from zero, from a redshift of 0 up to a maximum redshift, which can be taken to be 6, for example. It depends on this term that I haven't said anything before, but this is basically a Gaussian, a log-normal distribution for the width, the intrinsic width of the fast radial burst, which is related to the width that we will observe. And it depends on the integral of the Schechter function that I showed in the plot before. So as we can see, this expression, this function, will actually depend on the field of view of the telescope and the minimal luminosity. But now the minimal luminosity is actually related to the minimum flux density and the signal to noise ratio. So we'll have basically 3 variables here. One of them, well, basically, if we have all the details of our telescope and if you define a signal to noise ratio, we can determine what's the detection rate for this given telescope. And then for bingo, well, we can have this very nice plot here, which shows the FRB detection rate per day and the field of view of the telescopes and the minimum flux density given Janskis. So basically here we have several different radio telescopes. Most of them are operating now. Unfortunately, Arecibo is no longer with us. As we can see, Bingo here will detect, for example, for a signal to noise ratio of 5, can detect, for example, 1 FRB each 4 or 5 days, for example, and it will be better. I mean, it will give more detections per day than some of the telescopes, for example, including Parkes, which was the first one to detect FRBs. Well, now we can see some other results if we vary the signal to noise ratio. So if we take different values for the signal to noise ratio, we can see here the detection rate for different surveys. Well, actually, this is not the detection rate, but this the mean time elapsed between two detections in given hours. So for example, CHIME will detect an FRB each 1.5 hours if it detects an FRB which has, if it has a signal to noise ratio larger than 3. And CHIME leads the detection, the number of detections in terms of FRBs. But we can see here that Bingo has a very good prospect to detect FRBs, given that it's not his main scientific goal, but it can give very good results, very good number of detections when compared to other instruments. Well, now actually this plot was, in order to calculate this plot, we assumed a flat spectrum, which means that we assumed that this alpha, this power over here, is 0, because this simplifies the calculation a lot, and a lot of those values plotted here for these telescopes assume this flat spectrum. Now, we can take different values for this spectrum index as we take here, and then we can compare the detection rate of for this, as a function of alpha, when compared to detection rate for the flat spectrum, considering different signal to noise ratios. And as we can see, for example, the detection rate is 1.5 times larger than for a flat spectrum, and for an alpha of 4, for example. There's something. Okay, yeah, actually, I'm almost finishing. Thanks, João. Well, now this result, since we are assuming a spectral index different from 0, this depends also. Okay, so now this depends also on the the high frequency and the low frequency that is emitted by the source. As I mentioned before, we assumed in this plot that the high frequency was 1400 megahertz and the low frequency 400 megahertz. But then we also calculated these results for different bandwidths of production for the FRB. So for example, we took this higher band between 1980 megahertz and 980 megahertz. And there's another band over here. Both of them gives a bandwidth of 1 gigahertz. And when we use these different frequencies, what happens to this spectrum is that it changes a bit. So for example, in one case, this curve goes up, and then this curve goes down. And in the other case, is the opposite way. So this curve goes up and this curve goes down. But in the end, the difference between the detection rates from between this lower band and this higher band is only 2.5. So roughly speaking, this shows that if we assume the bandwidth for the emission for the source that we assume, and it doesn't change much the results. Well, now what I showed here was the detection rate calculated by this expression, and we assumed a simple Gaussian beam for the telescope. And now we are doing several follow-up works. We are doing several more detailed works regarding the detection of FRBs. So for example, we are calculating the detection rate using the Bingo antennas pattern and assuming several outrigger telescopes. As it was mentioned yesterday, outrigger telescopes are smaller versions of a given telescope, and using interferometry techniques, outriggers, along with the main telescopes, for example, in the Bingos case, can be used to localize precisely the FRBs, because one of the main challenges is not only to detect FRBs, but to precisely localize them in the sky. And in order to do that, we can use interferometry and the outriggers that are being developed, are being investigated in the collaboration. In this way, we can precisely pinpoint the location of FRBs. And this is a very important task, a very important goal, in order to understand where FRBs come from, and then we can understand better this very interesting phenomena. Now, in order to calculate precisely this detection rate, Marcelo developed a very good code to simulate FRBs. It's called FRBLIP. So it basically populates the sky with a simulation of FRBs, and then we can put the antenna pattern of Bingo and then the outrigger telescopes in cross correlation, for example, and really count how many FRBs are really detected by Bingo. And this will give a very good measurement, a very good indication of how many FRBs Bingo can detect. Besides that, we can use FRBs to constrain cosmology, as is being explored by Xuejian, Yusan, and André in another ongoing work. So basically, we have a lot of work going on Bingo, and we hope that in the next month, maybe we'll have new results in the literature, so stay tuned. Finally, I'm just gonna say that although Bingo was built and designed to detect BAO, Bingo can be used to understand this very interesting and still unknown phenomenon called fast radio bursts and contribute decisively to astrophysics science. Finally, this work is part of the Bingo Stage 1 working group, which deals with not only the possibility of detect FRBs, but also deals with the raw data, the time domain data, and the data analysis. And it has a lot of members, about 30 members, active and more sporadic members. And well, thank you very much for your attention. That's it.
Okay, thank you, Ricardo. Thank you so much for the nice presentation. Once we are a little bit out of the time, I will ask for the next speaker to present, but then we can share some questions after the end of the presentations together. Okay, thank you again, Ricardo. Okay, so as the next and last speaker, I'd like to invite Camila to share her screen with us. Oh, thank you, Camila.
I think, can you see my screen?
Yes, we are seeing, but oh, okay. Now it's in the presentation mode.
Oh, okay. Great.
Okay. So thank you, Camila, for coming and attending our invitation. So Camila Novaes, she's postdoc at INPE Brazil. She's also a member of the stages 2 and 3 of Bingo collaboration. And today she's going to present us the seminar Prospects of Measuring the Baud Signal with Bingo Telescope. Thank you so much, Camila. So the word is yours.
Thank you, João. I'd like to thank you and the other organizers for such a nice meeting. What I would like to show you here is what we have been doing in the sense of trying to predict what to expect from Bingo measurements in the context of measuring the BAO signal. So from previous talks, we we had very nice explanations about what are the BAOs, the baryon acoustic oscillations. So I will not go through the details here. I would just summarize in one very short slide. We see here this feature, the BAO feature in the galaxy distribution, for example, where this distance is this scale is the distance, is how far the baryons traveled until matter and the photons decouple. So this signal is not only imprinted in the CMB, but also in the distribution of the large scale structure because of this previous coupling between them. And but how we can measure this feature, the BAO? In the case of the CMB, we have, for example, here in the right, we see here the angular power spectrum with a clear signal of the BAO scale here in the first peak. And from the large scale structure, here we see the first statistically significant detection of the BAO with a clear peak here, showing an excess of a probability of finding two galaxies separated by this scale, the BAO scale. So, and here also from the matter power spectrum. So, but as I said, how exactly we can measure this feature, and more important, how we can measure it for the 21 centimeter signal from Bingo. So to do this, I will just summarize very briefly two possible ways to do this. The first one is using not what we call weakly model dependent approach, where we don't fit a cosmological model, but we can use like this expression on empirical equation to fit the BAO feature. For example, in these two works, in these two plots I'm showing here. And at the end, we will find, through this methodology, we will find the angular position of the BAO feature. And here an example of how we can use it to constrain cosmological models and combine it with other observables to constrain cosmological models. Here are just a compilation of BAO measurements from several works, and we see that with Bingo we will be able to contribute here in this region. And another approach that Elisa also mentioned, that is, you can fit a cosmological model. You can use a template constructed based in a given cosmological model, and you can fit it to the clustering estimated from your data. For example, here we have examples from calculated from the Dark Energy survey, where they fit the template model to their two-point angular correlation function, here for the 3D correlation function, and here for the angular power spectrum. And here on the right side, you can see an example of a forecast that have been done for the 21 centimeter signal, but as will be observed for by the SKA. So we see here for several redshift. So this is the approach we are using now for our forecast for Bingo. So at the end, what we will what we are interested in here is this alpha parameter that appears here in blue, which gives us a measure of the of how the BAO peak is shifted with respect to a given cosmological model. For example, here in the right, we see a compilation of several measurements of this alpha parameter that is basically this relation appearing here, where d is the angular diameter distance and the r is the acoustic scale at the drag epoch. And here we have this measurement compared with a given cosmological model that here comes from Planck constraints. So again, we'll be able to fill out this region here with the bingo measurements. And here on the left side, I just would like to show you how this alpha parameter can change if you change the cosmological, some of the cosmological parameters. So, but how we can do this, how we can do this measurement for the future data that will be provided by Bingo. To predict how well Bingo will be doing this, we use simulations that try to reproduce what Bingo will observe, and we consider not our analysis. We consider 30 frequency beams or redshift beams. We will consider the same sky coverage and the instrumental noise as expected by Bingo, as well the foreground contamination and the beam size, which we consider here as a Gaussian shape. And we have now the facility of testing our methodology over two sets of simulations. The one from flash simulations, from where we can produce a large set of simulations. All the results I will show you here are comes from these simulations, but we have also been applying our methodology over the mocks that Jiajun showed us previously today earlier. So using these large set of simulations, we calculated the clustering statistics, which here are the angular power spectrum. We are considering the two of them, the angular power spectrum in harmonic space and the 2-point angular correlation function, the W of theta that I show you here. So in the case of the angular power spectrum, we use the approach called pseudo power spectrum, pseudo CLs, because since we have partial sky survey, we have to correct the CLs by the mask. And in the case of the W of theta, we do an analysis very similar to what have been done for CMB, which is basically you can just average, we can calculate this statistics just averaging the multiplication of the temperatures between of two pixels separated by a given angle, a given distance theta in the sky. So here in the left we see the CLs expected, the theoretical expectations for the CLs on the higher and the smaller redshift beams. And we see that the BAO wiggles appears in very different range of multiples. And in the right, we can see the expectations for the 2-point function. So we see here that the angles, the theta BAO expected from the range of redshifts being we observe goes from 5 to more or less 16 degrees on the smaller redshifts. So calculated the clustering statistics from each of our simulations, we have to use what I told you before. We have to use cosmological model, a template to fit our measurements. So here what we are doing is we construct a template for the P of K, the matter power spectrum, based on the linear power spectrum, for example, calculated using class, which is this red curve here. And we use this other term that is the same power spectrum, but without BAOs. So because of this, we have this black curve very smooth with no wiggles. And this parameter here, the sigma parameter, it just introduces the effect from the nonlinear evolution that tends to smooth the BAO features, the BAO wiggles. So constructed this P of K, we can just have this expression like Andre showed us before. Here we are using the UCL cell code to generate these CLs based on this P of K we constructed using this expression. So from this P of K, we can then finally get our templates for the angular power spectrum written like this, and for the 2-point function written like this. For the CLs, as I said, we just have to project the P of K. And for the 2-point function, the W of theta, we can use this relation between the CLs and the 2-point function, and we can write this template where we have these 4 free parameters, B, A0, 1, and 2, and the alpha parameter that is exactly that alpha parameter I mentioned before. That is the one that we are interested in estimating here, that is our goal here. And just to remind you what is this alpha parameter, comes from this relation. And here the fiducial cosmology we are considering in the analysis is this one, that is the cosmology used to produce the mock simulations, as Jun showed us. And just to be consistent, all the flash simulations are also using this cosmology. So at the end, since we are constructing the templates with the same cosmology used to generate the simulations, we expect the alpha parameters measured from each of the simulations to be near to 1. So to do this, to fit these templates to each of our simulations, to fit the templates to the clustering estimated from the simulations, we use a maximum likelihood estimator, which is basically constructed from the chi-square, where we compare the model, the template model, with the clustering, each of the clustering estimated from the simulations, and using the covariance matrix from each case constructed from the simulations. So at the end, we will estimate these 4 last parameters for each of the bingo, for each of the beans that bingo will observe. But for the alpha parameters, we combine some of the beans so that we are able to increase the significance of our detection. This is a very, very nice facility from bingo, because as this combination of several beans helps a lot improving the result, the significance, and the error bars. So what I will show you here are the results from basically 3 cases. Because from bingo we have a certain facility of dividing in several different ways the bands. So here I will test how well our methodology works in each case. In the first case, we have a binding of the beans in linear in frequency, so that each of the 30 beans have the same delta E frequency. And the analysis, the statistical analysis fitting the templates will combine each 10 consecutive beans. In the second one, we use this same idea of binding frequency, linearly in frequency, but we will combine 12, 10, and then the last 8 redshift beans. And in the last case, instead of binding linearly in frequency, we do this linearly in redshift. And again, combining each 10 consecutive redshift beans. We will also perform some robustness tests just to check how is the best way to estimate the clustering statistics in terms of which binding is better. If we use, for example, a binding in multiples of 10 and 0.5 degrees for the case of the 2-point function, or another case. Our fiducia configuration here will be this one, the case one here, combined with this binding for multiples and for the 2-point functions, the 2-point function, which seems to be the less, which seems to give us the results of less bias. So these are the results. First, using what I told you here, this binding for the 2 estimators, we compare the 3 cases. The case 1, 2, and 3 in blue, red, and green. So what we have here is basically the histogram of the alpha parameters estimated from each of the 1,500 Flask simulations. So each alpha here in this plot is obtained by fitting 10 the first 10 redshift beans. Here in the second column, we fit the second 10, sorry, this is just for the blue case, because for the red case, we have from the 12 first redshift, and here the case 3, as I explained. But the idea is, in the first column, we have analysis from smaller redshift. In the second column, the intermediate redshifts, and the last column, we have results from higher redshifts. We see that all of the cases appear to be very consistent between themselves, with slight better results from this green one. But at the end, what we choose from here to use is the blue one, which is a linear binding frequency, and analyzing each of the 10 consecutive redshift beans. And yes, just to be clear here, what we are trying to show you from these plots is that, for example, for the higher redshift beans, we have better results. But why we have these better results? We see that average of parameter from each of the cases, they are much more in agreement with the expected result, which is alpha equals to 1, than in the other cases. And also in parentheses, we can see the number of simulations we are considering. But why we are not considering all the 1,500 simulations here? Because the other simulations, in this case, we don't have BAO detection at all. So we don't have any significance for this BAO detection in those simulations. So we just exclude them. So what we can conclude here is, for small redshifts, we have a smaller probability of detecting BAO from bingo than from the higher redshifts. This is the significance of our detections. Again, we have the comparison of the three cases, and basically we have the histogram of the significance estimated for each of the simulations and for each of the estimators. We see that for when compared the two estimators for the smaller redshift beams, we have a much better results, a better result from the 2-point function with a higher significance of the detection. And but for the higher redshift, although both estimators show better results for the higher redshifts, when we compare the two estimators for higher redshifts, the CLs gives us better significance of our detection. As I told you, we also performed some robustness tests, trying to choose the better configuration when calculating the clustering estimators. And these cases I highlight in gray. These are the configuration that seems to be a bit less biased from all the cases we consider. When I say less biased is, for example, here we see that for delta L equals to 10, we have this alpha parameter, this average alpha parameter, more near to 1 than for 15, for this width of 15. And the same case here in the right for the 2-point function. So, but all the previous results that I showed you, they are not that realistic. Actually, they are on ideal. They are from ideal case where we don't include the noise and foreground contamination. So what we have, our idea was to test how each component influences the analysis separately. So when we include the white noise, what we have summarizing the results, what we have is a larger error bar. This is not seen from, this is not that expressive from smaller redshift beams for both estimators. We see that the error bars are slightly larger than we had before, but not very much. But when we observe this last column with the results from the higher redshifts, we see that the impact of the noise is higher, and this can be explained because of that plot that I showed you before. This one, you can see that for higher redshifts, the BAO wiggles go until a multiple much higher than for smaller redshifts. And in this case, and since the white noise is dominating the larger multiples, the impact is much larger on is much higher on the last redshift beams. But still, it is very promising and very, very nice. And here, the same for the significance of the detection from each of the simulations, each range of redshifts from each of the simulations. And again, we can see quite agreement between, we don't see that impact, a huge impact on the smaller redshifts, but we see a large impact on the larger redshifts. what we see here is that at higher redshifts, the significance of our detection will have a larger impact than for small redshifts. And the last part, which is very, very important, and which we are working on now, is the inclusion of the residual foreground contamination. Our idea is to include the foreground contamination as well as the white noise, and go through component separation. So we will have a huge collaboration between the groups from stage 2 and the stage 3 to deal with this point. And the idea is to perform these BAO measurements and see which is the impact of the foreground residuals. So just to summarize and conclude here, I would like to call the attention for the facility of using different simulations and test and scrutinize the methodology that we are using. And also we have seen from the results that the clustering estimators, each clustering estimator shows different sensitivities to each redshift bins, although both of them showed a better performance on the higher redshifts. And this is very nice because you have a kind of complementarity between them. And also we have showed here that our results show that for small redshifts, it will be more difficult but not impossible to measure the BAO feature with Bingo, but the results for intermediate and higher redshifts are very promising, and we could this way confirm the capability of Bingo in measuring the BAO signal from 21 centimeter signal. So the good point here is that now we have a first version of a pipeline that we can use to look for these BAO features, which we expect to improve in many ways until we have the data. And of course, as I said, testing in the most realistic scenarios as possible is very important, and we are doing this just now. That's it. Thanks.
Okay, thank you so much, Camila, for such a nice presentation. Thank you very much indeed. So before we start the questions for the speakers, I just would like to invite the general coordinator of the Bingo collaboration, Professor Elcio Vidala, to tell us about the next steps of Bingo and next perspectives. So thank you so much, Elcio, for your time. Thank you for being here with us today again. And the word is yours to talk about a little bit about the future of Bingo.
First, I would like to thank all of you again for this great effort and for all the contributions, these nice seminars. I hope that we can really establish Bingo this year. But this is obviously not completely possible in view of our pandemic and the situation in the country. But I am basically very confident that we shall be able to have our projects in good terms by the end of the next year. And this will be this is feasible. Of course, that depends on the support we shall have from the various people that promised us to help. But if we can obtain the proper help, I think at the end of next year we shall have a project which is right on the track to get the radio telescope working, then our commissioning, and then the first slides on real physics and real observations by the beginning of 2023, probably. On the other hand, we have already one of the outriggers basically working by the wonderful work of the people from UFCG. And we don't have the first slides, but the first, not the first slides in terms of physics, but certainly something in terms of testing and observations of the material that we have in hands to see if it is really working and can be tested and can be used as a proper way of observing FRBs. So these are the prospects. As I said, I am confident that we can fulfill them. Thank you all very much, and have a nice bingo collaboration for the next few years. Thank you very much.
Thank you so much, also. Thank you, people, for tears, and thank you so much, also, for nice speak, and for your time. I would like to thank all of our speakers. I guess that the seminars today, they were amazing, and they fulfill our idea when we built this event of showing what we are producing for Bingo for the entire collaboration. So I guess that the collaboration now can see really clear the science that has been discussed and has been done in each of the stages. So I'd like to open this space for questions for the speakers and comments. So people, you are free to talk or to interact with us at the web chat. Well, and we have a question here, which came from the YouTube by Clécio Lima. I guess it is for Ricardo. I hope he still is here. The question is there any relation between FRBs and GRBs, the gamma ray bursts?
No, I mean, they are different phenomena. So basically, gamma ray bursts are bursts, but it's in the gamma ray frequency. So they are much more energetic. They share, I mean, so maybe they have similar origins, but it's not still understood. There are some similarities in a more mathematical way. For example, one of the distributions that I showed for the redshift, one possibility is to use a Poisson distribution. And this Poisson distribution is used basically because GRBs follow a Poisson distribution, and then it's more or less expected, and sometimes the data agree that maybe FRBs also follow this distribution. So there might be some relation in the future that we are still not aware of. As for example, I think now it's 3 or 4 years ago, that a binary neutron star merger produced the gravitational waves and electromagnetic waves. So at that time, we discovered that gravitational waves and electromagnetic waves can be produced by the same phenomena. They may have, and then they have the same speed. But yeah, maybe we can find out in the future some relation between these two phenomena. Thank you. Thanks for that question. Very interesting.
Thank you so much, Ricardo. Is there any other questions for the speakers?
Sorry, I have maybe one question for Mathieu Hamzi. So I just want to know, for the GNUC method, is there any public available version for the GNUC that can be adapted potentially for generic 21 centimeter telescope, or is it currently still primarily used specifically on Bingo?
Hi, Tianyu. So no, there is no public version. There are several versions out there. The versions which are used on CMB are not exactly the same which are used on intensity mapping. And currently the code which is run here is within the Bingo collaboration.
Okay, thank you.
Is there any other questions? And let me check here the YouTube channel again, if you have anyone. No, let me check the chat again. Okay, I think we don't have any further questions, but well, feel free to contact us by email if you have any questions, and we can send the questions for the speakers. Okay, and well, I guess we are a little bit over time, and so maybe this is the reason behind the absence of questions. But I would like then to start the closing section of the event, and I starting this by saying thank you for everyone who watched this event here at Zoom and at YouTube. I would like to thank also the members of the Chinese team, through Professor Bing Wang, who helped us to organize this event, inviting several distinguished guests for the opening ceremony. We would like to thank all authorities who supported the Bingo event. I have some data here collected about the event to share with you. So we have a really nice audience on Zoom and on YouTube. We have almost 200 people attending Zoom in day 1 and day 2, adding the audience of the Zoom room. We also had in day 1 audience about 90 or 18, between 18 and 100 people at YouTube. And today we have something like average of 20 people watching us live in YouTube. About the registrations, we had 268 participants registered for this event. So I guess it was a really nice audience for Bingo. We also had an important repercussion of Bingo in the press here in Brazil and also in China. So I would like to thank you all for being here today with us. And it was really a pleasure for me to help with the organization of this event, of being the chair of this event today. So thank you for being here, and thank you for giving me this opportunity. It was really an honor to be with you. So with these words, I guess we can finish the event. So if any of the PIs here at the Zoom room would like to say something, feel free to use your microphone. Well, okay then. So I guess we can finish here. Thank you very much, friends. It was a pleasure. See you in another opportunity. Bye, Lisa. Thank you for everything.
Thank you. Bye-bye.
Bye. Bye-bye.
Bye.